in the deepest, darkest voids of the universe. Beyond the invisible, intangible, yet powerfully felt nothingness, lies an incredible reality. I invite you on a journey that will change the course of history, uncover the most fundamental secrets of existence, and reveal one of the greatest scientific discoveries of all time. The quantum vacuum, that invisible ocean of energy, is not just empty space. It is a vast reality where millions of invisible particles are born, die, and recreate the universe itself, pushing the limits of our perception. Today, we will lift the veil on the truth that billions of people are curious about, that there is something in the void. Get ready, because after this, you will never look at the universe, existence, or yourself in the same way again. This is the beginning of a great awakening that will shape the future of science and humanity. One of the fundamental principles of quantum mechanics is that the vacuum is not an absolute nothingness, but a field in constant vibration. While classical physicists view the vacuum as the absence of particles and energy, in quantum field theory, every point is a dynamic stage where virtual particle pairs briefly appear and disappear. These vibrations are a consequence of Heisenberg's uncertainty principle. The uncertainty relationship between energy and time allows for energy fluctuations in space, thereby transforming nothingness into an ocean of energy. The existence of vacuum energy provides us with critical clues about the origin and fate of the universe. For example, these quantum fluctuations, known as zero-point energy, can trigger a wide range of phenomena, from the evaporation of black holes to the accelerating expansion of the universe. Dark energy, the Casimir effect, measured at the subatomic level, provides a real measure of the energy of the vacuum between two metal plates, thereby experimentally proving the concept of emptiness. Thus, emptiness emerges as a hidden source of power in nature. On the other hand, the fact that the quantum vacuum is not completely empty opens up new horizons in technology. Theoretically, zero-point energy could offer an almost unlimited source of power. However, in practice, harnessing and utilizing this energy conflicts with fundamental principles such as the second law of thermodynamics and the conservation of energy. Nevertheless, researchers are working on how vacuum energy can be controlled in artificial micro and nanoscale devices. These studies could open the door to future nanomechanical systems and high-efficiency energy conversion technologies. In conclusion, the quantum vacuum is not empty. Rather, it is a living environment that enables the emergence of matter and energy. When we look at the deepest structure of the universe, we cannot fully understand any physical event without considering emptiness. Therefore, what we call empty is actually one of nature's richest and most mysterious addresses. Quantum field theory is based on the idea that every particle is represented by a field: electrons, photons, quarks. All these particles emerge from the excitation of appropriate quantum fields. However, due to Heisenberg's uncertainty principle, the relationship between energy and time allows for fluctuations, which in turn leads to the emergence of temporary entities known as virtual particle pairs in the vacuum. These pairs briefly appear as particle-antiparticle pairs, e.g., electron-positron, before disappearing again. So, where do they come from? Fundamentally, the universe itself is built on a foundation of quantum fields filled with zero-point energy. This energy is the source of virtual particles through vacuum fluctuations. The energy of the fields temporarily manifests itself in the form of real particles. The current standard model successfully describes these processes, but they are still experimentally difficult to control or measure. Virtual particles are not just a theoretical tool. They also have experimental effects. The best-known example is the Casimir force. The vacuum between two parallel metal plates applies a false, attractive force to the plates because it blocks the fluctuations of the medium. This force arises from the decrease in virtual particle pressure and is strong enough to be measured at sub-meter scales. Thus, virtual particles experimentally demonstrate the real effects of the quantum vacuum. Today, researchers are exploring the control and application of virtual particles to develop quantum information processing, nanomechanical circuits, and perhaps even techniques for directly harnessing zero-point energy. Though this field is still in its infancy, virtual particles show us that the universe holds limitless potential. Space is not a static medium in the classical sense. The quantum fields within it are constantly vibrating. Every point experiences random bursts of energy called vacuum fluctuations. These bursts emerge from the Heisenberg uncertainty principle. The uncertainty between energy and time allows for constant energy borrowings in the vacuum. These short-lived borrowings lead to the creation and annihilation of virtual particle pairs and fluctuations in the field's amplitude. This bubbling structure influences the macroscopic properties of the universe. For example, Hawking radiation near black holes combines with the strong gravitational field of vacuum fluctuations to create real particles, ultimately causing the black hole to slowly evaporate. Similarly, dark energy, which accelerates the expansion of the universe, may be a global reflection of zero-point energy. Thus, microscopic boiling drives macroscopic cosmic dynamics. Although it is difficult to observe these fluctuations directly in the laboratory, their indirect effects can be measured. Subtle structural changes predicted by quantum electrodynamics, such as the Casimir and Lamb shifts, confirm the microscopic effects of vacuum fluctuations. In modern quantum optics experiments, even the wave functions of photons shift slightly due to the structure of the vacuum, one of the most concrete indications of the boiling nature of empty space. Theoretically, understanding exactly how quantum fluctuations work is crucial for developing grand, unified theories and quantum gravity. The interaction of these fluctuations with the geometry of space-time could represent the biggest leap forward in understanding the conditions at the beginning of the universe and the internal structure of black holes. The boiling vacuum is therefore one of the most productive areas of research in modern physics. The Casimir effect is one of the most concrete examples experimentally demonstrating that the quantum vacuum is not empty. First proposed by Hendrik Casimir in 1948. This effect states that when two conductive plates are placed very close together, a repulsive force arises between them due to the vacuum. This force is caused by the restriction of the wavelengths of virtual particles allowed in the space between the plates. Since more quantum waves vibrate on the outer side, less wave pressure is created on the inner side, causing the plates to appear to push against each other. The beauty of this situation is that it shows that not only particles, but also empty space can create physical effects. While classical physics cannot explain this result, quantum field theory predicts that vacuum fluctuations can generate physical forces. Measurements have confirmed that the Casimir force increases as the distance between the plates decreases. The fact that this force becomes measurable even at distances as small as 1/1000th of a millimeter suggests that the energy of the quantum vacuum can be extremely intense. The Casimir effect is not merely a subject of experimental curiosity. It is also a phenomenon with significant technological implications. In micro and nanoscale devices, such as microelectromechanical systems, MEMS, unwanted Casimir forces can cause circuit components to stick together. As a result, modern engineering designs must take quantum vacuum effects into account. In other words, the quantum vacuum is not just a philosophical problem, but also a practical one. Thanks to the Casimir effect, we can directly observe that emptiness is a thing. This reveals that the zero-point energy of quantum fields is not just an abstract assumption, but a physical reality that can interact with other things. It is now an almost certain physical reality that quantum emptiness contains energy. However, the question of why we cannot directly feel this energy reveals the great difference between quantum mechanics and classical observation. Zero-point energy is the minimum energy level found at every point in space. And this energy is like a fundamental ground state that ripples over everything in the universe. However, this energy is universal, homogeneous, and isotropic. So it does not create any differences as long as it remains constant. Humans are sensitive to changes in the physical world. For example, changes such as the movement of an object, an increase in temperature, or the arrival of sound can be detected. However, the zero-point energy in the quantum vacuum is like a constant and unchanging background. We can only sense its presence through differences or fluctuations in this energy, as in the Casimir effect. When the environment changes, it is possible to interact with this constant energy level. That is, changes can be detected. Furthermore, this energy has no counterpart in classical physics. It does not have a directly perceptible effect like gravity or electromagnetic forces. Therefore, it cannot be directly felt. However, its existence can be proven through indirect means. For example, small shifts in energy levels at the atomic level, such as the Lamb shift, are explained by the vacuum's influence. Such precise experimental measurements make the effects of the energy in empty space visible. To summarize briefly, the reason we cannot sense the energy of empty space is that it is a constant background and cannot be directly perceived by classical physical senses. However, this does not mean it is ineffective. Even massive events like the expansion of the universe may be shaped by this energy, even if we are unaware of it. While modern cosmology is working on several theories to explain the origin of the universe, one of the most intriguing is the hypothesis that the universe may have spontaneously emerged from a quantum vacuum. According to this idea, a Big Bang may have occurred as a result of a process such as quantum tunneling within the vacuum energy. In this process, energy fluctuations within the void may have created a rupture large enough to give rise to time and space. One of the fundamental concepts underlying this idea is that quantum fluctuations can initiate a real physical state when they are sufficiently large. Through quantum tunneling, energy barriers can be overcome, allowing a universe to emerge from nothingness. Cosmologists use this idea, especially when integrating it into the early universe model of inflation theory. According to this model, the universe was formed when the vacuum suddenly expanded and then began to expand rapidly. This scenario also provides a physical answer to the question, why is there something rather than nothing? If the quantum vacuum is a structure that can potentially give birth to universes at any moment, then our universe may be just one result of these processes. In this case, multiverse hypotheses also come into play. Perhaps many universes like ours were born from the same quantum vacuum in different ways. Although not yet experimentally confirmed, this idea provides a more scientific foundation for questions about the origin of the universe. Observations such as cosmological background radiation, vacuum fluctuations, and the nature of cosmic structures support this hypothesis. If the universe really did arise from a vacuum, then emptiness could be considered the mother of the universe, both giving birth to it and still containing infinite possibilities. The concept of dark energy, which was proposed to explain the accelerating expansion of the universe, is one of the greatest mysteries of modern cosmology. However, at the heart of this mystery lies another question. Could dark energy be related to the quantum vacuum? the zero-point energy that exists in a vacuum. Physicists have long thought that these two concepts may actually be different expressions of the same phenomenon. This is because dark energy is defined as a mysterious form of energy that is evenly distributed throughout space and exerts a negative pressure, much like the theoretical effects of zero-point energy in the quantum vacuum. This idea first emerged in the mid-20th century and led to a return to Einstein's concept of the cosmological constant. Einstein had added a constant to his equations because he assumed the universe was static. This constant represented a type of vacuum energy that causes the curvature of space-time. However, when it became clear that the universe was expanding, he referred to this constant as the biggest mistake of my life. Yet, in 1998, observations revealed that the universe's expansion was accelerating, bringing Einstein's mistake back into the spotlight and linking it to dark energy. This energy behaves like a property of space itself, like energy hidden within the void. However, there is a major paradox here. When the energy of the void is calculated theoretically according to quantum field theory, the resulting values are 120 quadrillion times greater than the observed dark energy density. This is one of the greatest inconsistencies in the history of physics and remains unsolved. This discrepancy either indicates a fundamental flaw in our theories or suggests that dark energy must be explained by a different, as yet unknown mechanism beyond vacuum energy. At this point, many physicists argue that we need new physical theories to explain dark energy. If dark energy is indeed the same as vacuum energy, then the fate of the universe is directly tied to the nature of empty space. This is because this energy exists equally at every point in the universe and, over time, becomes more dominant, accelerating cosmic expansion. This clearly shows us that empty space is not merely the absence of something, but an active player in the cosmos. According to general relativity, matter and energy bend space-time. However, one of the truths revealed by quantum theory is that energy can exist even when there is no matter, meaning that the vacuum is not empty. This raises an important question if there is energy in the void. Can this energy also bend space-time? The answer is yes, it can. This is because Einstein's field equations are sensitive not only to mass, but also to energy density. Therefore, zero-point energy can affect the fabric of space-time, even if it has no mass. This effect is included in the equations under the name cosmological constant and determines the rate of expansion of space-time. This phenomenon can be particularly important in the early stages of the universe. Inflation theory was developed to explain the rapid expansion of the universe in its first moments, which occurred thanks to a type of vacuum energy. This energy was provided by a field that inflated space. This shows that space is not merely a passive structure, but an active player capable of directly shaping space-time. In other words, what we call space has the capacity to alter the geometric and physical structure of the universe. Another consequence of this idea emerges in black hole physics. For example, the phenomenon known as Hawking radiation is explained by quantum vacuum fluctuations around a black hole, causing virtual particles to transform into real particles. This process leads to the eventual evaporation of black holes. This demonstrates that space is not merely a placeholder. It is a dynamic entity with the potential to alter even the most intense and powerful structures in the universe. Space is no longer just something that doesn't take up space. It is the very pen that draws the shape of the universe. The Higgs field is a quantum field proposed in 1964 and confirmed by experiments at CERN in 2012. Its most striking feature is that it gives mass to particles. However, the intriguing aspect here is that the Higgs field is present throughout the entire universe, even in empty space. This field has a specific value even in a vacuum where no particles exist. And this constant value enables particles to gain mass through their interaction with it. This demonstrates that empty space is not a completely passive field, but contains active and continuously operating fields. The fact that the Higgs field is constant and universal reveals that space is actually an extremely orderly and consciously functioning stage. Without this field, the fundamental particles of the universe, such as electrons or quarks, would have no mass. This would make the formation of atoms and, consequently, matter impossible. In short, even the concept of mass, which forms the basis of physical existence, can only exist thanks to an invisible field operating in space. Furthermore, there's a direct link between the Higgs field and the quantum vacuum. Even when the Higgs field is at its lowest potential energy, i.e., in its most stable state, it still has a value other than zero. This situation shows that there is a difference between the vacuum of the universe and true emptiness. Perhaps the vacuum we currently live in could evolve into another vacuum with lower energy. This possibility leads to catastrophic scenarios known as vacuum collapse, which could theoretically result in all physical laws of the universe changing in an instant. In conclusion, the Higgs field is like a quantum machine operating in the void. It is invisible, silent, yet it determines the identity and existence of every particle in the universe. Quantum tunneling is a mysterious and impressive phenomenon that classical physics cannot explain. In short, it means that a particle passes through a potential barrier that is higher than its energy, rather than overcoming it. This is impossible according to classical logic. If you throw a ball down a hill and its energy is lower than the hill's height, the ball will roll back up. But at the quantum level, things don't work that way. This is because particles are not just point-like entities, but also probability waves. These waves can extend all the way to the other side of a barrier. If the wave function is non-zero on the other side of the barrier, then there is a chance that the particle will appear there. That is, tunneling occurs. This situation takes on an even more interesting dimension in the quantum vacuum, because the vacuum we refer to is not actually a void where nothing exists. On the contrary, it is a bubbling quantum sea where virtual particle-antiparticle pairs are constantly forming and disappearing, and energy fluctuations occur. The tunneling effect becomes more likely in this turbulent environment. Particles can use these fluctuations to overcome potential obstacles before they happen. Some physicists even suggest that the universe itself was born from a tunneling event in the quantum vacuum. This tunneling effect has many real-world applications. For example, nuclear fusion occurs at the center of the sun thanks to this effect. Despite being electrically repelled, two positively charged protons can come together and fuse through tunneling. Similarly, devices such as tunnel diodes, which form the basis of modern electronic devices, and scanning tunneling microscopy (STM), rely on this quantum phenomenon. Each of these examples demonstrates that space is not merely a passive field, but also a passageway that enables particles to move between places. Although it sounds like science fiction, the idea of extracting energy from the quantum vacuum has intrigued both theoretical physicists and advanced technology researchers for years. This is because the quantum vacuum is not a nothingness devoid of energy, as commonly believed. Rather, it is a constantly fluctuating energy field filled with zero-point energy. These fluctuations occasionally produce measurable effects. For example, the Casimir effect causes a force to arise between two plates due to the energy difference in the quantum vacuum. This is a very small but measurable interaction and is directly related to the energy of the vacuum. However, directly and continuously extracting this energy or converting it into a power source presents significant theoretical challenges. The second law of thermodynamics sets the limits on the flow of energy from disorder to order. If vacuum energy could be used unlimitedly, this law would be violated. Furthermore, this energy field is so symmetrical that it is directionless. That is, it is nearly impossible for a device to continuously draw this energy in a specific direction. According to our current understanding of physics, extracting energy from the vacuum means disrupting the natural order of fluctuations, which is tantamount to interfering with the fundamental workings of the universe. Nevertheless, some theories and experimental proposals suggest that this energy may be usable in the future, at least under certain conditions. For example, with the development of quantum computers or superconducting technologies. The possibility of processing this energy at the micro level is being discussed. Although such ideas are still highly speculative, the potential of the quantum vacuum as an energy source expands our scientific horizons. Absolute zero is the lowest temperature physically possible, minus 273.15 degrees Celsius. At this temperature, according to the laws of classical physics, all motion should cease. However, quantum physics offers a big surprise at this point. Even if the temperature is zero, energy cannot be completely zero. This energy is called zero-point energy, and the quantum vacuum comes into play precisely at this point, even when absolute zero is reached. Fluctuations continue in quantum systems because Heisenberg's uncertainty principle states that quantities such as position and momentum cannot be known precisely at the same time. This means there is constant quantum vibration. These vibrations show that the void is not empty at all. Electrons around atomic nuclei cannot remain completely motionless even at absolute zero. Similarly, fields do not completely disappear at this temperature. On the contrary, zero-point oscillations continue. For example, helium gas remains liquid and does not freeze even at temperatures very close to absolute zero. This behavior is due to the zero-point energy still causing matter to move at the molecular level. This is one of the real-world effects of the quantum vacuum. This phenomenon has profound implications, not only for laboratory experiments, but also for cosmology. This is because the earliest stages of the universe also had extremely low temperatures. However, even during these periods, the active presence of the quantum vacuum plays a role in the operation of physical laws. Quantum fluctuations may be the source of the density fluctuations that formed at the beginning of the universe. These fluctuations later laid the groundwork for the formation of galaxies, stars, and planets. For most people, time is a universal and constant flow. It moves forward, never stops, and works at the same speed everywhere. However, this understanding is an illusion left over from classical physics. At the quantum level, and especially in quantum space, time takes on a much more complex dimension because time is not just a process measured by the ticking of a clock. It is a dynamic experience shaped by particle interactions, field fluctuations, and uncertainties. The question of how time works in space forces us to question the very definition of time. How can we tell if time passes when we assume that there is nothing in space? In fact, to determine whether a system evolves over time, we need to observe a change within it. However, if what we call space is constantly fluctuating at the quantum level, that is, if virtual particles are constantly forming and disappearing, then this means that there is a process, and therefore time is functioning. More strikingly, according to some quantum gravity theories, time is a derivative quantity that emerges together with space. That is, if the structure of the vacuum changes. Time itself may exist in different forms or not at all. This leads us to the idea that time is not a fixed ground, but a dynamic property, especially at the Planck scale. Even the continuity of time disappears. There may be discontinuous transitions between moments. This is the basis of the concept of timelessness explored in quantum gravity theories. Some physicists argue that time did not actually exist in the first moments of the universe, but was merely a configuration of energy fields. In other words, time may be a structure that potentially emerged from quantum space. In conclusion, it would be misleading to say that time does not exist in space, but our classical understanding of time may not apply there. The existence of time is shaped by the structure of space. If there is a process even where there is nothing, then time is there, but perhaps in a form very different from what we know. In classical physics, space is truly empty. It is a plane at absolute zero, devoid of matter and energy, where not even light can pass. This definition of space is based on Newton's idea of absolute space, which is a fixed stage independent of its contents. However, quantum mechanics radically shakes this concept. According to quantum field theory, space is not a stage but a direct actor. It is a physical entity that exhibits behavior and interacts with matter. Quantum space is the minimum energy state of various fields. But even this state is not completely motionless. This is because Heisenberg's uncertainty principle states that fields can never be completely fixed at zero in terms of energy and time. This creates a ground where the vacuum constantly fluctuates and virtual particles appear and disappear instantaneously. It is this property that makes the quantum vacuum a completely different reality from the classical vacuum. While classical space is dead and passive, quantum space is a living, active, and interactive stage. This difference is not only evident in the microscopic world, but also on a cosmic scale. For example, in classical space, light waves simply pass through. In quantum space, even those waves interact, bend, and create effects such as vacuum polarization. Additionally, the quantum vacuum contains fields such as the Higgs field, which confers mass to particles. In this context, space is not merely empty. It is the medium where the fundamental constants of matter, energy, and physics are determined. Thus, there is not only a quantitative, but also a qualitative difference between the classical and quantum vacuum. Quantum vacuum is not a place where something is missing. Rather, it is a sea of quantum possibilities where everything is possible. The fact that the energy of empty space is not zero is one of the most fundamental results of quantum mechanics. And this fact is a critical point that determines how the universe works at both the micro and macro levels. In classical physics, a system with no energy is considered to be zero. However, things are not that simple at the quantum level. This is because Heisenberg's uncertainty principle states that we cannot know both the energy of a field and its change over time with absolute certainty. This uncertainty makes it physically impossible to reach zero energy. This is why the energy of empty space is not exactly zero. This energy is called zero-point energy, and this energy is not just a theoretical concept. It is a physical phenomenon with directly measurable effects. For example, the Casimir effect confirms the existence of this energy. Two conductive plates attract each other even though there is nothing between them. This is explained by the fact that the space outside the plates contains more energy. Thus, the energy of the void is one of the most striking experimental proofs that the void is not nothing. Moreover, this energy, which is not zero, also affects universal constants. In quantum field theory, even the minimum energies of fields have profound effects on physical reality. Therefore, the The energy of space becomes one of the fundamental building blocks, not only of particles, but also of time, space, and even the fate of the universe. In particular, the magnitude of the cosmological constant depends on this energy. This constant determines the expansion rate of the universe. Thus, the energy of space can directly influence all cosmic scale processes. The human mind naturally tends to think that nothing can come from nothing. But quantum physics overturns this intuitive assumption. Because what we call the quantum vacuum is not nothing in the true sense. It is a constantly fluctuating quantum field structure that carries the invisible seeds of matter and energy. In this field, virtual particles constantly appear and disappear. Normally, these particles are instantly annihilated to maintain energy balance. However, under extreme conditions, such as during the early universe at the moment of the Big Bang or near black holes, these temporary entities can become permanent. This transition from transience to permanence, the transformation of virtual particles into real particles, occurs through energy transfer. Energy can be converted into matter according to the equation E equals mc squared. Thus, sufficiently intense energy can create a particle-antiparticle pair. These pairs usually disappear immediately. But under certain conditions, if the balance is disrupted, one may become permanent. In the first seconds of the universe, these energy densities were so high that real matter could form from the quantum vacuum. The existence of the universe may have begun with this explosion of emptiness. This process can still be observed today in some cosmic events. For example, particles can emerge from fluctuations in the quantum vacuum near the event horizon of black holes. This mechanism explains the process known as Hawking radiation. As one particle falls into a black hole, another can escape, causing the black hole to lose mass. This means that even the most powerful dark entities in the universe can be destroyed by particles born from the quantum vacuum. Virtual particles are temporary entities that appear in the quantum vacuum. Unlike physical particles, they cannot be measured or directly observed. Their existence is only possible for a very short time, because according to the Heisenberg uncertainty principle, the uncertainty between energy and time allows for large energy fluctuations in a short period. In other words, the system's energy can be borrowed for a very short time, but this debt must be repaid. This explains why virtual particles disappear suddenly. They are temporary, borrowed entities that exist for a brief moment without violating the laws of nature. The fleeting existence of virtual particles does not render them insignificant. On the contrary, these transient entities play vital roles in the functioning of nature. For example, the behavior of electromagnetic fields is influenced by the constant creation and annihilation of virtual electron-positron pairs. This phenomenon can even affect the actual mass and charge of electrons. In fact, a significant portion of a proton's mass originates from the energy C created by these virtual particles. Thus, despite being invisible, virtual particles shape the most fundamental properties of the universe. This transience is also the foundation of the dynamism of the quantum vacuum. The vacuum is constantly vibrating, and virtual particles emerge through these vibrations. However, the total energy of the system must be conserved. Therefore, when a virtual particle emerges, it must be immediately annihilated. Otherwise, nature's energy balance would be disrupted. This rule is vital for the consistency of physical laws. At first glance, the vacuum of space may seem like a static foundation. However, quantum mechanics challenges this perception. According to quantum field theory, The vacuum state is not absolute emptiness, but the minimum energy level of fields. These fields, such as the electromagnetic or Higgs field, continue to exist even in empty space. This means that space is never completely static because these fields fluctuate spontaneously. These fluctuations are called quantum fluctuations and form the variable structure of space. This variability is not limited to the microscopic level. It also has macroscopic effects on a cosmic scale. Small changes in vacuum energy can affect the expansion rate of the universe. In fact, according to some theories, sudden changes in vacuum energy could abruptly alter the fundamental structure of the universe. This hypothesis is called a vacuum transition. If the current vacuum state is metastable, it could transition to a lower energy state, which could lead to a vacuum catastrophe where the physical laws we know would suddenly break down. However, the fact that the vacuum is not static demonstrates the dynamic nature of nature. If the vacuum were completely static, most physical processes would not occur. The oscillations of fields, particle interactions, and the expansion of the universe would cease. Thus, it is not stability, but variability that is natural. Quantum mechanics shows us that even the most seemingly static things are constantly changing from within. This is one of the most important insights into the fundamental workings of the universe. The fact that the vacuum is not static reminds us that the universe is a process. At every moment, everywhere, there is a constant restructuring at the microscopic level. If there were no such thing as a quantum vacuum, the universe would most likely be completely different from what it is today. It might not even exist. This is because the quantum vacuum is not just emptiness. It is an invisible energy and field structure that forms the infrastructure of the universe. This structure makes it possible for particles to emerge, interactions to occur, and the laws of physics to function. Without it, there would be no mass for particles, nor would there be interactions between forces. The formation and evolution of matter would be completely disrupted, especially in the period following the Big Bang. Quantum vacuum energy was the primary driving force behind the expansion of the universe, known as cosmic inflation. This expansion initiated the universe's growth, and as energy density decreased, matter began to form. Without this vacuum energy, the universe would have remained much smaller, denser, and more chaotic. Galaxies, stars, and even the concept of time might never have emerged in this order. In short, the engine of existence was hidden in the quantum vacuum. Furthermore, the quantum vacuum continues to play an active role in today's universe. Thanks to virtual particles, the balance of forces between atoms is maintained. Interfield transitions are enabled, and energy transfer becomes possible. All these processes occur with the active participation of the void. Without this structure, electrons could not remain stationary around the nucleus. Chemical bonds could not be formed. Life, matter, and energy would lose their meaning. Everything would turn into a chaotic soup of particles. In conclusion, the quantum vacuum is not merely nothingness. It is an indispensable foundation for existence. The expansion of the universe has been accelerating, especially in recent times. This observation has greatly surprised scientists. Normally, gravitational force pulls all matter in the universe toward each other and is expected to slow down expansion. However, observations show the opposite. Galaxies are moving away from each other at an increasing speed. To explain this contradiction, scientists introduced vacuum energy, also known as dark energy, which is the energy of the quantum vacuum. This energy originates from the vacuum itself and exerts a repulsive force on the universe. The quantum vacuum is filled with virtual particles, and this structure corresponds to energy in in Einstein's equations. This energy exists at a constant density in every unit of space. Therefore, as the universe expands, this energy does not disperse because the energy comes from the nature of space, not from matter. As a result, more space means more vacuum energy. This creates a vicious cycle that accelerates expansion. That is why the expansion of the universe is accelerating rather than slowing down. This situation may also determine the fate of the universe in the future. If vacuum energy remains constant, the universe will continue to expand indefinitely. However, if vacuum energy increases over time, galaxies, star systems, and even atoms could disintegrate. This scenario is called the Big Rip. On the other hand, if vacuum energy decreases at some point, the universe could begin to collapse again. All these possibilities show how powerful a force the seemingly empty space actually is. The quantum vacuum plays a decisive role not only in the beginning of the universe, but also in its future, because this invisible sea of energy is one of the fundamental forces that shapes the structure of space, the flow of time, and the fate of matter. In particular, the amount of vacuum energy determines how the universe will expand and whether this expansion will eventually come to an end or continue indefinitely. Therefore, to understand the fate of the universe, we must first understand the nature of the quantum vacuum. If vacuum energy remains constant, the universe gradually cools, expands, and eventually reaches a state known as heat death. At this point, stars fade, galaxies drift apart, and energy transfer ceases. No interactions remain in the universe. Absolute darkness and stillness prevail. However, this is not the quietest end. In a scenario where vacuum energy is unstable, the universe could suddenly transition to a lower energy vacuum state. In this case, the laws of physics would change, and all existence would cease. This vacuum transition is akin to an erasure of existence. Furthermore, it is possible that vacuum energy could increase over time. In this scenario, everything in the universe rapidly moves apart, with galaxies, stars, planets, and even subatomic particles disintegrating. This scenario is known as the Big Rip and predicts that everything will inevitably come to an end. Thus, whether static or dynamic, the void is one of the greatest forces shaping the future. Invisible, silent, but absolutely effective. Therefore, looking at the quantum vacuum is not only looking at the past, but also at the future. It is the invisible chain that connects the two ends of time. The concepts of the quantum vacuum and dark energy are related but distinct concepts in modern cosmology. While the quantum vacuum refers to energy fluctuations in the fundamental structure of space, dark energy is a mysterious type of energy proposed to explain the accelerating expansion of the universe. Scientists believe that dark energy may actually be a type of energy originating from the quantum vacuum. This is because the energy in the quantum vacuum could potentially create a repulsive force that spreads throughout every point in space and accelerates the expansion of the universe. However, there is a problem here. Theoretical calculations estimate the energy density of the quantum vacuum to be incredibly large when compared to observations. In other words, the theoretical vacuum energy is approximately 10 to the power of 120 times greater than the energy required to explain the accelerating expansion of the universe. This enormous discrepancy is one of the greatest paradoxes that modern physics must resolve. This is called the vacuum energy problem and represents a discrepancy between quantum mechanics and general relativity that has yet to be fully resolved. Despite this paradox, The fact that energy fluctuations in the quantum vacuum determine the dynamic structure of the universe is one of the main focuses of research for scientists trying to understand the nature of dark energy. Dark energy, which affects the future fate of the universe and the speed of its expansion, may be a complex reflection of these invisible quantum fields. Therefore, the quantum vacuum continues to play a key role in solving one of the most fundamental mysteries of the universe. Although the quantum vacuum is perceived as an invisible, matterless field, it actually reveals itself through its effects. One of the most concrete examples of these effects is the Casimir effect. The Casimir effect is a force that arises between two metal plates placed very close to each other and is caused by a pressure difference created by virtual particles in the vacuum. In other words, these quantum fluctuations, which we cannot see, have a physical effect on matter, and this effect can be measured experimentally. In addition, small shifts in the energy levels of atoms, such as the Lamb shift, can also be used to detect the existence and nature of the quantum vacuum. The energy levels of electrons around the atomic nucleus change slightly due to the influence of the vacuum. This is an important fact that quantum electrodynamics has successfully explained and confirmed through experiments. Thus, it is shown that there is actually a continuous energy and particle fluctuation in space. Furthermore, virtual particle effects observed in particle accelerator experiments also reveal the dynamic structure of the quantum vacuum. In very high-energy collisions, energy fluctuations can transform into real particles, allowing the energy oscillations within the quantum vacuum to be indirectly observed. All these findings prove that what we call nothingness is actually a physical reality and the building block of the universe. In short, although the quantum vacuum cannot be seen, its existence is clearly revealed by its effects on matter. The quantum vacuum is an invisible energy field that forms the fundamental fabric of the universe. Unlike the classical physics concept of empty space, the quantum vacuum consists of continuous energy fluctuations. These fluctuations occur at the smallest scales of the universe and are considered the building blocks of space. The quantum vacuum plays a central role in the emergence of the fundamental forces and particles of the universe. This energy field influences the expansion of the universe and the distribution of matter and energy, creating significant effects on a cosmic scale. For example, the expansion rate of the universe can vary due to vacuum energy, and the fate of the universe may even depend on the magnitude of this energy. Thus, the quantum vacuum plays a key role not only in the microscopic, but also in the macroscopic shaping of the universe. The structure of the quantum vacuum is explained by quantum field theory, an important part of modern physics. According to this theory, all particles are excitations of quantum fields, and these fields constantly vibrate in what we call empty space. These vibrations provide the basis for the formation and annihilation of particles. Therefore, beneath the visible surface of the universe, the quantum vacuum is in constant motion, and this motion supports the existence of the universe. Finally, the quantum vacuum holds the key to unlocking the mysteries of the universe. Its relationship with concepts such as dark matter and dark energy, which are not yet fully understood, continues to push the boundaries of science. The quantum vacuum is a critical concept for understanding both physical reality and the dynamic structure of the universe. Virtual particles are short-lived particles that constantly appear and disappear in the dynamic structure of the quantum vacuum. Unlike real particles, they cannot be directly observed, but their existence is supported by quantum field theory and experimental observations. The continuous production and annihilation of virtual particles demonstrate that the vacuum is actually an energy-filled structure. These particles influence the total energy balance of the universe. Energy conservation can be temporarily violated at the quantum level due to uncertainties, and the emergence of virtual particles is an example of this. Thus, vacuum energy is not a static value, but a dynamic and variable energy source. This energy could be the source of the forces driving the expansion of the universe. The effects of virtual particles cause the energy in the quantum vacuum to manifest in various physical phenomena. For example, observations such as the Casimir effect and the Lamb shift demonstrate the indirect effects of virtual particles on matter. This indicates that virtual particles are an integral part of the fundamental energy structure of the universe. Black holes are known as the most dense concentrations of energy and mass in the universe. The quantum vacuum, on the other hand, is an energy field that exists everywhere and at all times. The quantum vacuum around black holes has much more complex interactions than previously thought. Stephen Hawking's theory revealed that black holes can evaporate due to the influence of the quantum vacuum. This process is known as Hawking radiation and explains how black holes lose energy and shrink over time. Near black holes, virtual particles form in pairs. Normally, these pairs annihilate each other within a short time. However, in the region near the event horizon of a black hole, one of the pair may fall into the black hole while the other escapes and carries energy out. This demonstrates that quantum vacuum fluctuations interact directly with black hole physics. This interaction provides clues about how classical gravity might merge with quantum mechanical rules. How energy and fluctuations in the quantum vacuum behave around black holes is one of the most important research areas in quantum gravity theory. This represents a critical step toward understanding the harmony of the fundamental forces of the universe. When we think of space as one of the fundamental building blocks of the universe, it is actually not empty at all. According to quantum field theory, space is not a complete void, as commonly believed, but an infinite source of energy, fields, and potential. All the matter and energy we observe in the universe originate from space, and the potentials hidden within it act as raw material in the formation and evolution of the universe. The quantum fields within space constantly vibrate, and these vibrations enable particles to emerge. Thus, the building blocks of the universe are nourished, grow, and exist within this empty environment. In short, the question of whether space is the invisible but most real raw material of the universe is one of the deepest and most exciting questions in modern physics. Space is completely different from matter. The concept of raw material here is different from the classical understanding because there are no physical particles in space. But there are potential and energy fluctuations. These energy fluctuations enable the continuous birth of virtual particles, which temporarily appear and disappear. In this sense, space is an infinite energy reservoir necessary for creating the building blocks of the universe. This energy, which exists everywhere in the universe, determines the distribution of matter and energy in the universe. In other words, space is the fundamental raw material that makes the shaping and vitality of the universe possible. Understanding this situation opens new doors to the origin and evolution of the universe. If space is the raw material of the universe, then the expansion of the universe and mysterious phenomena such as dark energy are also related to the energy structure of space. The properties of the quantum vacuum can explain how the universe was shaped and why it looks the way it does. This invisible structure of space gives rise to the ever-changing dynamics of the universe, which play an important role in cosmological models. Viewing space as the raw material of the universe may be an important step in understanding the fundamental nature of existence. Ultimately, the question of whether space is actually nothing has become a thought that is now being questioned not only by physicists, but even by metaphysicians. Can't space be seen as a completely empty and energy-free area? Quantum theory shows us that this is not the case. In space, the constant vibration of quantum fields reveals that energy never disappears and is always in a state of fluctuation. These vibrations enable the accumulation of potential energy in space. This potential energy is one of the fundamental forces that shape the structure of the universe. Though it is invisible to the naked eye, space is not an energyless trap, but an invisible sea filled with energy. Therefore, the existence of potential energy in space is one of the most fundamental results of quantum physics and plays a critical role in the energy balance of the universe. To understand how potential energy is created in space, we need to look at the concept of the quantum vacuum. The quantum vacuum is a state in which the fundamental fields are at their lowest energy level, but not zero. Therefore, space is not the absence of energy, but a state close to zero, but still energetic. Quantum fluctuations cause this energy to fluctuate, thereby ensuring the accumulation of energy even in space. This energy plays a role in the expansion of the universe and the formation of matter. Potential energy in space is considered an infinite and dynamic source. The potential energy in space determines the fundamental dynamics of the universe. This energy may also be the source of dark energy, which accelerates the expansion of the universe. The relationship between consciousness and space is a complex topic that has been debated for years in both the physical and philosophical worlds. Some contemporary theories suggest that consciousness is not merely a product of brain activity, but that a universal field of consciousness may exist. This field is thought to be connected to the quantum vacuum, or space. Could emptiness, as a field capable of carrying energy and information, form the foundation of consciousness? This question creates both a challenging and fascinating area of research for scientists seeking to understand the nature of consciousness. If consciousness is connected to the quantum vacuum, this could redefine humanity's place in the universe and the meaning of existence. Quantum physicists explore the role of the vacuum while developing theories about how consciousness operates at the quantum level. The quantum vacuum is known as a field where energy and information-carrying fluctuations are constantly present. According to some interpretations, these fluctuations may influence the quantum-level processes in our brains, thereby linking the formation of consciousness to the vacuum. This assumption suggests that consciousness interacts not only with biological systems, but also with quantum fields. This approach strengthens the possibility that consciousness is a universal phenomenon and expands the boundaries of human consciousness. Studies that further deepen this relationship continue in the fields of quantum information theory and neuroscience. Theories that the quantum vacuum increases the information storage and processing capacity of consciousness also make possible forms of consciousness that transcend the limits of the human brain. If consciousness is connected to the void, it may not be just an individual experience, but part of a universal field of consciousness. This implies that there may be an energy and consciousness network at the foundation of existence. Ultimately, the possible connection between consciousness and space is a subject that challenges both scientific and philosophical boundaries. Confirming this connection could revolutionize our understanding of the universal nature of human consciousness and its integration with the universe. The large-scale structure of the universe, including the distribution of galaxies and dark matter, has been mapped through observations. However, these maps cannot fully reveal the invisible, fundamental structure of the universe. Could space be an invisible yet fundamental network that determines the fabric of the universe? The complex structure and energy of the quantum vacuum control the fundamental dynamics of the universe. And thus, space could function as an invisible map of the universe. This invisible structure could serve as a guide, determining how matter in the universe is distributed and moves. Does space, as the invisible map at the core of the universe, reveal the true architecture of the universe? This invisible map is a complex fabric woven by quantum fields and energy. The structure of this fabric influences the clustering patterns of galaxies and dark matter. Quantum vacuum fluctuations are one of the most fundamental elements determining the expansion and structural development of the universe. Therefore, space is an invisible network forming the skeleton of the universe. To understand the large-scale structure of the universe, it is necessary to decipher this mysterious map of space. This structure forms the big picture that determines the fate of the universe. The idea that space is the map of the universe opens up new areas of research in modern cosmology. Studies on the quantum vacuum and the energy of space are increasing in order to understand the invisible structure of the universe. Space is not just emptiness, but a fundamental guide that secretly shapes the behavior and dynamics of the universe. In conclusion, the question of whether space could be the invisible map of the universe is a critical point in understanding the fundamental nature of the universe. Beyond the superficial appearance of the universe, space forms its true architecture, and deciphering this architecture is a major step forward for cosmology and fundamental physics. As the invisible map of the universe, space can reveal the deepest secrets and structure of the universe. Therefore, the mystery of space is a key element in solving the secrets of the universe. Quantum mechanics and field theory tell us that space is not actually completely empty. In classical physics, space is thought of as a place where there is no matter, energy, light, or particles. However, quantum fields are in a constant state of vibration, and these vibrations show that energy never stops. Therefore, what we call vacuum is actually filled with invisible but moving energies. These energies manifest themselves as virtual particles that exist temporarily due to Heisenberg's uncertainty principle. Although these particles cannot be physically observed, their existence has been proven by experiments. Therefore, the quantum vacuum is not a void in the classical sense, but a dynamic field filled with energy. Energy fluctuations and virtual particles constantly appear and disappear within this field. This energy, which has existed since the early stages of the universe, plays a vital role in the expansion of the universe, dark energy, and the formation of matter. Thus, the quantum vacuum is considered the fundamental building block of the universe. This energy-filled quantum vacuum influences the macro-scale dynamics of the universe. The expansion of the universe, the movements of galaxies, and cosmic structures are shaped by this energy. In short, one of the forces behind the visible universe is the energy of the quantum vacuum. This shows us that we need to rethink the concept of space. In quantum field theory, each type of particle is represented by a field, and these fields constantly vibrate in space. These vibrations cause energy fluctuations, which, according to Heisenberg's uncertainty principle, manifest as temporary energy debts. These energy debts enable virtual particles to form instantaneously. Virtual particles are not permanent like real particles. They are very short-lived, unobservable, and constantly forming and disappearing energy packets. These particles exist thanks to the uncertainty between energy and time. In other words, the universe does not conserve energy. It temporarily borrows energy and uses it to create virtual particles. These particles have a lifespan of just a billionth of a second. But their interactions can influence physical events. For example, The Casimir effect is explained by the pressure of virtual particles formed in the space between two metal plates. The existence of virtual particles demonstrates the dynamic and complex structure of the quantum vacuum. Emptiness is not merely an invisible and intangible void, but also a reservoir of energy and information at the foundation of physical reality. The effects of these particles play a crucial role in the interactions of the fundamental forces of the universe and form the basis of cosmic developments. Ultimately, virtual particles are the key component in understanding the reality behind the void. Without them, the energy balance of the universe, the formation of matter, and quantum processes cannot be explained. Dark energy is a mysterious form of energy proposed to explain the accelerating expansion of the universe. Quantum vacuum energy is thought to be related to this dark energy. Energy fluctuations in the quantum vacuum show that space itself possesses energy. This energy acts as a propulsive force that accelerates the expansion of the universe and shapes its destiny. However, the amount of vacuum energy predicted by quantum field theories is incredibly large when compared to observations. This discrepancy is known as the cosmological constant problem. This situation indicates that the true nature of dark energy is still not fully understood. Nevertheless, most scientists point to the quantum vacuum as the source of dark energy. While dark energy accelerates the expansion of the universe, the quantum vacuum, as the fundamental energy field of the universe, fuels this process. This relationship is one of the most striking examples of how the macro-scale behavior of the universe is connected to micro-scale events in the quantum world. Energy fluctuations within the quantum vacuum are extremely important for the formation and evolution of the universe. These fluctuations cause the irregular distribution of matter and energy in the universe. After the Big Bang, these irregularities laid the foundation for the cosmic structure and paved the way for the formation of galaxies, stars, and planets. Energy fluctuations may also be the source of dark energy, which affects the expansion rate of the universe. The dynamic energy of the vacuum shapes the fabric of space and accelerates the expansion of the universe over time. Thus, this dynamic energy in the void directly influences the macro structure and destiny of the universe. At the same time, these fluctuations trigger particle formation at the micro level. Virtual particles emerge thanks to energy fluctuations in space. And this process ensures the existence of the fundamental particles of the universe. When we look at the moment of the universe's birth, the Big Bang, it appears that one of the most fundamental factors at the beginning was the energy fluctuations in the quantum vacuum. These fluctuations indicate the existence of energy levels that are never completely stable and stationary, even at infinitely small scales. It is these microscopic vibrations and fluctuations that form the core of the universe's large-scale structural elements. Initially, all matter and energy were distributed uniformly. But these energy fluctuations created tiny dips and peaks in the fabric of the universe. These building blocks grew over time through gravitational attraction, eventually forming stars, galaxies, and even galaxy clusters. Without these quantum fluctuations, the universe might never have achieved any structural diversity, remaining a completely flat and featureless sea of energy. More importantly, these energy fluctuations not only determine the structure of the universe, but also influence the very shape of time and space itself. The fabric of space-time stretches, bends, and expands with these energy changes within the quantum vacuum. Thus, the expansion dynamics and geometric structure of the universe are directly influenced by these microscopic movements. These small energy fluctuations are actually the spark that ignites cosmic scale events. From another perspective, These quantum vacuum fluctuations shed light on the deepest mystery of the universe. Why do we exist? Because the existence of this energy makes the universe's existence from nothing and the emergence of complex structures possible. Virtual particles are one of the most mysterious and fascinating phenomena of quantum mechanics. They are temporary bursts of energy that exist for a brief moment, shaping the energy structure of the vacuum. Yet they do not behave like real particles in the physical sense. The constant creation and annihilation of virtual particles provide a constant motion and vitality in the fundamental structure of the universe. This is far beyond our classical understanding, as the seemingly empty vacuum is actually a dynamic, living, and ever-changing environment. The existence of these particles influences many physical phenomena, from the stability of atoms to the interactions of quantum fields. For example, the transmission of electromagnetic forces that keep electrons bound to the nucleus is made possible by the existence of virtual particles. Without virtual particles, the bosons that carry the fundamental forces would lose their function, and thus atoms, and therefore matter, could not exist. Additionally, the effects of virtual particles have been directly observed in experiments such as the Casimir effect. The attractive force that arises between two very close metal plates due to a decrease in vacuum energy is created by virtual particles altering the density of the vacuum, thereby generating a physical force. This demonstrates that quantum field theory and the vacuum are not merely mathematical abstractions, but have real physical effects. Therefore, virtual particles are the invisible architects of physical reality, thanks to their constant and mysterious movement. The universe is more than just empty space. It is alive, dynamic, and in a state of constant change. When the expansion of the universe was discovered to be accelerating, particularly in the last decade, scientists began discussing a new form of energy known as dark energy. Dark energy is a mysterious force present in the fabric of space that drives the universe's rapid expansion. Energy in the quantum vacuum is one of the strongest candidates for dark energy. Vacuum energy creates a type of negative pressure that exists in space itself and determines the dynamics of the universe. This energy accelerates the expansion of the universe. That is, as space expands, vacuum energy causes the universe to expand even faster. Thus, empty space is not just a place that contains no matter or light, but also an active agent that determines the fate of the universe. The energy of the quantum vacuum plays a fundamental role in explaining the unknowns in the history of the universe's expansion. However, an important paradox arises here. When quantum field theories calculate the theoretical value of vacuum energy, the result is approximately 10 to the 120th power times larger than the value obtained from astronomical observations. This discrepancy is one of the greatest mysteries and research topics in modern physics. This means that the exact role of quantum vacuum energy in the expansion of the universe is still not fully understood. In conclusion, the energy in the quantum vacuum plays a critical role in the expansion of the universe. This energy is a mysterious force that determines the speed of the universe and shapes our cosmic destiny. The quantum vacuum, defined in classical physics as space where nothing exists, has taken on a completely different meaning in modern quantum mechanics. Quantum field theory reveals that this emptiness is actually a field where an infinite number of virtual particles are constantly being created and destroyed, and energy is constantly emerging. The amount of energy here is theoretically immeasurable, even approaching infinity. So why and how can such an energy source exist? This is directly related to the uncertainty principle of quantum mechanics. The uncertainty between energy and time suggests that energy values can fluctuate greatly in short intervals. Thus, the vacuum is theoretically like an infinite well that continuously emits energy. However, this concept of infinite energy is in stark contrast to the laws of classical thermodynamics. According to the law of conservation of energy, it is impossible to produce infinite energy. This situation seriously challenges the conservation of energy, one of the cornerstones of modern physics. From another perspective, the possibility of infinite quantum vacuum energy calls into question the mechanism of the universe. If such infinite energy truly exists, why doesn't the universe suddenly disappear? Why is there a constant balance between energy limits? These questions have driven scientists to develop new theories at the intersection of quantum field theory, gravity, and cosmology. Perhaps the answers to these questions lie in quantum gravity theories, often referred to as the theory of everything. The fundamental forces of the universe, gravity, electromagnetism, and the strong and weak nuclear forces are complex systems that have been in balance since the beginning of the universe. It is believed that the energy and fluctuations of the quantum vacuum play a critical role in the formation of these forces. The quantum vacuum is essentially a vast sea of energy in which the fundamental force-carrying particles exist and interact. The energy fluctuations within this sea led to the differentiation of forces in the early universe. Initially, the four fundamental forces were unified into a single force. But the energetic structures and vibrations within the quantum vacuum triggered their separation. Even the slightest change in energy affected the distribution of matter and energy in the universe, determining the nature and intensity of the forces. Thus, the energy of the vacuum played a central role in shaping the fundamental laws of physics. For example, the Higgs field interacts with the quantum vacuum and enables particles to acquire mass. This demonstrates that the vacuum is not merely empty space. It is a complex and dynamic environment where matter and forces are interconnected. Energy fluctuations shape the properties and interaction patterns of particles, thereby forming the current structure of the universe. In conclusion, the energy and fluctuations of the quantum vacuum are an indispensable factor in the emergence of the fundamental forces of the universe and matter. Black holes are the most dense, mysterious, and extreme objects in the universe. Observations and theoretical studies reveal that the properties of the quantum vacuum have a direct effect on the formation and evolution of black holes. The quantum vacuum surrounding black holes is an environment where events that transcend classical physics occur. First, quantum processes known as Hawking radiation cause black holes to slowly evaporate. In this process, virtual particle pairs form in the strong gravitational field of the black hole. And as one of them falls into the black hole, the other escapes, emitting energy. This leads to black holes losing energy over a long period of time before completely disappearing. The presence of quantum vacuum energy and virtual particles directly determines the life cycle of black holes. In addition, the dynamics of the quantum vacuum around black holes create complex effects on the curvature of space-time and the event horizon at the edge of black holes. This situation allows black holes to be understood as a bridge between quantum mechanics and general relativity. This field is one of the most critical research topics in modern physics, and a full understanding of the role played by vacuum energy here would mean rewriting the fundamental laws of the universe. In conclusion, the quantum vacuum is a fundamental determinant not only in the formation of black holes, but also in their evolution, radiation emission, and ultimately, their demise. The expansion of the universe is one of the most mysterious and exciting topics in modern cosmology. The quantum vacuum creates an energy density through virtual particles that constantly appear and disappear in empty space. This energy density can alter the structure of the space-time fabric, thereby changing the rate of the universe's expansion. In particular, the mysterious force known as dark energy may be a macroscopic manifestation of quantum vacuum energy. Energy fluctuations in the quantum vacuum may have triggered the inflation process that occurred in the early stages of the universe. During this process, the universe expanded at an incredible speed in a fraction of a billionth of a second. This rapid expansion determined the current distribution of fundamental particles and forces. Thus, the energy properties of the vacuum directly shaped both the structure and dynamics of the universe. The current increase in the expansion rate of the universe, i.e., accelerated expansion, may indicate that quantum vacuum energy is constantly acting as a propulsive force in space. This energy raises questions about how the universe will evolve in the future, whether it will be infinite or come to a halt one day. Once the nature and effects of quantum vacuum energy are understood, all assumptions about the fate of the universe may need to be rewritten. In the first moments of the universe, matter and antimatter were created in almost equal amounts. But today, matter is much more abundant. Quantum vacuum energy fluctuations may be one of the mysterious reasons behind this imbalance. The rapid creation and destruction of virtual particles and antiparticles may have influenced the matter-antimatter separation in this early process, resulting in the excess of matter observed in the universe. The quantum vacuum directly affects the mass, decay, and stability of particles. Energy fluctuations in the vacuum alter the behavior of particles, leading to different ratios of matter and antimatter. This process is critical to our understanding of the universe's current structure, because if the universe were filled with antimatter, our existence would not be possible. Furthermore, vacuum energy and fluctuations can break the symmetry laws of the universe. This symmetry breaking is known as CP violation in physics and is considered one of the fundamental causes of the matter-antimatter asymmetry. Energy changes in the quantum vacuum can pave the way for such violations to occur. Cosmic microwave background radiation is radiation from approximately 380,000 years after the Big Bang, and is one of the most important clues about the early history of the universe. The quantum vacuum plays an indirect but critical role in the formation and evolution of this radiation. Energy fluctuations in the vacuum caused small irregularities in the distribution of matter in the early universe. And these irregularities formed the basis for the temperature differences observed in the cosmic microwave background. These small irregularities provided the foundation for the formation of galaxies and other cosmic structures. The effect of quantum vacuum energy helps us understand how the large-scale structure of the universe took shape. Additionally, the role of vacuum energy in the expansion of the universe is reflected in the observed properties of the microwave background radiation. Another important point is the complex connection between the anisotropies observed in the cosmic microwave background and the quantum vacuum. This connection is a direct indication of the macroscopic effects of quantum fluctuations at the beginning of the universe. Thus, the mysterious structure of the vacuum creates the first light of the universe and its current cosmic map. Ultimately, the relationship between the quantum vacuum and the cosmic microwave background radiation provides deep insights into the structure and dynamics of the universe, spanning a timeline from its beginning to the present day. The mystery of quantum vacuum energy holds tremendous potential, not only for theoretical physics, but also for technological developments. The controlled use of this energy field has the potential to be an unlimited and clean energy source for humanity. In the future, it may be possible to solve the energy crisis, facilitate space travel, and usher in a new technological age by harnessing quantum vacuum energy. In addition, quantum vacuum manipulation could enable the development of next-generation computing technologies, ultra-precise sensors, and communication tools. A deep understanding of this energy and the fields that form the foundation of quantum computers could exponentially increase our computing capacity and offer data processing capabilities at speeds unimaginable today. Furthermore, groundbreaking technologies such as gravity manipulation could emerge through the control of vacuum energy. This could enable the bending of the space-time fabric, making concepts from science fiction films, such as traveling at speeds close to the speed of light, time travel, or interdimensional travel, a reality. Furthermore, direct control over quantum vacuum energy could initiate one of the greatest technological leaps in human history. The concept of an infinite energy source could transition from mere fantasy to a tangible physical principle. Engines, devices, and even buildings powered by this energy could offer efficiency and sustainability far surpassing current energy systems. As humanity's dependence on energy is redefined, global economies and social structures could undergo fundamental changes. Quantum vacuum energy offers a promising gateway to completely eliminate fossil fuels, protect the environment, and restore our planet's ecological balance. The energy and fields offered by the quantum vacuum could form the basis for next-generation computing technologies. Quantum computers offer processing power and speed far beyond that of classical computers. And through the manipulation of the quantum vacuum, our information processing capabilities could increase exponentially. This technology could accelerate the development of artificial intelligence, open new horizons in solving complex problems, and revolutionize scientific discovery. These quantum-based systems, which go way beyond the limits of today's supercomputers, will empower humanity in data analysis, simulation, and modeling. The energy of the quantum vacuum can also affect gravity and the structure of space-time. In the long run, this could open the door to technologies that let us travel at speeds close to the speed of light. Space travel could enable us to explore the solar system and beyond at speeds unimaginable today. The realization of science fiction themes, such as time travel or portals to different dimensions, could completely transform humanity's relationship with the universe. This would mark the beginning of a new era, not only technologically, but also philosophically and existentially. Future applications of the quantum vacuum could go beyond energy production to revolutionize fields such as healthcare, communication, and materials science. For example, super-sensitive sensors and imaging techniques could utilize fluctuations in the quantum vacuum to enable the early detection of diseases. In communication technologies, the manipulation of quantum vacuum fields could herald a completely new era in terms of security and speed. In material science, quantum vacuum effects could enable the development of new generations of supermaterials by providing control at the atomic level. Furthermore, controlling quantum vacuum fields could bring extraordinary technologies such as gravity manipulation to life. With the bending of the space-time fabric, concepts such as time travel and interdimensional travel, which are currently only theoretical, could become scientific reality. Such revolutionary developments could rewrite humanity's place in the universe and the limits of existence. The impact of quantum vacuum technologies could change not only the scientific world, but also the entire human perspective, from culture to philosophy, beyond energy, communication, and transportation. Quantum vacuum manipulation could enable a new form of existence. The interaction between the human body and energy fields could lead to the development of new health paradigms. Perhaps it will be possible to achieve seemingly impossible goals, such as increasing mental capacity, accelerating learning processes, or delaying aging by using the quantum vacuum. As the boundaries between humans and technology become increasingly blurred, The quantum vacuum will be at the heart of this transformation. The controlled use of quantum vacuum energy can also fundamentally change sustainability and environmental balance by providing a clean and inexhaustible energy source to prevent the climate crisis caused by fossil fuels. This technology can enable ecosystems to revive, along with a revolution in energy production. Science-based solutions can be offered to protect our planet and leave a livable world for future generations. This will be one of the greatest steps taken in human history with ecological awareness. Understanding and manipulating quantum vacuum fields can reveal new forms of communication for humanity. Thanks to quantum entanglement, instant and secure communication may become possible. This could lead to the complete renewal of global information networks, ensuring universal and unrestricted access to information with new communication technologies. As the boundaries of the information age dissolve, the development of societies and global cooperation could accelerate. The quantum vacuum could become an invisible bridge connecting humanity more closely together in the deepest void of the universe, invisible to the eye, intangible, yet enveloping every particle of our existence. The quantum vacuum is like an infinite melody beating at the heart of existence. It is a unique stage where energy, waves, and particles dance between existence and nothingness. This stage does not merely shape our physical realities or limit our scientific understanding. It transcends time and space, pushing the boundaries of human comprehension, surpassing our dreams and assumptions, and drawing us into the infinite embrace of the unknown. The quantum vacuum is not a simple void. It is a grand narrative that weaves the fabric of the universe, the building blocks of our existence, the mysterious web of life and death, creation and destruction, like a library. It opens the doors to another universe on every shelf, carries the light of the unknown on every page, and opens the doors to infinity with every word. And we are but small travelers within this narrative. As our eyes gaze upon the glittering stars and our hearts wander through the depths of the unknown, we take steps toward new realities beyond the limits of our perception. As the mystery of the quantum vacuum is unraveled, we will find ourselves in the unknown song of the universe, feel the invisible rhythm swaying at the farthest points of existence, and lose ourselves in time only to be reborn. Infinity is not an end. It is an endless cycle of beginnings and discoveries. Within this cycle, the meaning of our existence will be rewritten, and our thoughts, dancing with the unknown, will set sail for new horizons. And thus, in the vast, deep, and enchanting mechanics of the quantum vacuum, we will not merely be spectators, but also writers of the story of infinity within the universe. Part of an endless fairy tale traveling between light and shadow. This fairy tale will continue forever, with every new discovery, every new question, and every new answer. It will recreate itself, grow, and continue to exist. That is precisely why the quantum vacuum is not just a physical phenomenon. It is a way of life, a way of thinking, the deepest and most fascinating connection between humans and the universe. Your eyes may tire, your mind may expand. You may forget the flow of time because here, every word, every sentence opens the door to a journey lost in infinity. And as you pass through that door, you will discover not only the universe, but also yourself in infinity, in the infinity of existence. Reality is stranger than we imagine. Science is the most powerful tool we have to understand that strangeness. 2.5 million light-years away, a galaxy 4 times larger than our own is racing toward us at 250,000 miles per hour. The Andromeda Galaxy contains 1 trillion stars, countless worlds, and mysteries that challenge everything we thought we knew about the universe. Today we witness stellar nurseries where baby stars are born in cosmic violence, explore planets where diamonds rain from methane skies, and encounter black holes so massive they could swallow our entire solar system in seconds. Our journey takes us through cosmic storms, past gravitational whirlpools, toward civilizations that might have risen and fallen a billion years before Earth even existed. Prepare yourselves. We begin. Our spacecraft engines ignite with the power of 1,000 suns as we break free from Earth's gravitational embrace. The blue marble that has been humanity's home for millions of years shrinks to a pale dot behind us, a single pixel of collective memory, then disappears entirely into the cosmic darkness. We are now truly alone in the void, beginning the longest journey any conscious being has ever attempted. The first challenge hits us immediately, not as a physical threat, but as a conceptual weight, the sheer scale of what we are attempting. To reach Andromeda, we must travel a distance so vast that light itself, moving at 186,000 miles per second, takes 2.5 million years to make this journey. If we could drive there in a car at highway speeds, never stopping, never sleeping, it would take us 30 billion years. The dinosaurs would still be ruling Earth when we finally arrived, and our own sun would have long since died. But we have technology beyond current human imagination. Our vessel bends space and time around itself, creating a bubble of warped reality that allows us to slip between the normal rules of physics. We accelerate not through space, but through the fabric of space-time itself. The stars around us begin to shift and blur, their light bending into chromatic arcs as we approach speeds that would have been impossible just moments before. This is not about brute force. It is about finding a loophole in the laws of nature, a way to fold the map instead of walking across it. As we leave our solar system behind, we pass through the Kuiper Belt, where ancient chunks of ice and rock drift in eternal darkness. These are the leftover building blocks of our solar system, frozen in time for 4.5 billion years, silent witnesses to the birth of our world. Pluto, once considered our 9th planet, appears as a lonely sentinel guarding the edge of everything we have ever known. Its heart-shaped glacier a fragile, frozen farewell. Beyond Pluto lies the Oort cloud, a spherical shell of icy objects that extends nearly a light year from our sun. This is where comets are born, in the frigid depths where temperatures drop to just a few degrees above absolute zero. It is not a belt, but a ghostly sphere, a halo of potential worlds and frozen water that marks the true gravitational boundary of our solar system. We are entering a region where the sun's influence barely reaches, where the space between objects is so vast that a collision is nearly impossible. The nearest star to our sun, Proxima Centauri, glows like a red ember in the distance. It would take a conventional spacecraft over 70,000 years to reach it. But we pass it in what feels like minutes. Its faint, angry light a fleeting reminder of another star's quiet story. We are now in interstellar space, the vast emptiness between star systems, where matter is so sparse that you could travel for millions of miles without encountering a single atom. This is where most space travelers would feel the crushing weight of isolation, the profound loneliness of being adrift in an ocean of nothingness. But we push forward with purpose. The Andromeda Galaxy beckons from across the cosmic ocean, its spiral arms slowly rotating in a dance that has continued for billions of years. We are no longer bound by the limitations of our species or our world. We are explorers of the infinite, and our destination contains wonders that will challenge every assumption we have ever made about reality itself. The real journey is just beginning. We enter the local void, a region of space so empty it defies comprehension. Here, between the galaxy clusters, matter exists in concentration so low that an entire cubic meter of space might contain only a single atom. The temperature drops to just a few degrees above absolute zero, and the only light comes from distant galaxies billions of light years away, their ancient photons stretched and tired from their long journey. This is cosmic loneliness on a scale that breaks human understanding. If Earth were placed in the center of this void, our night sky would be completely black, except for the faint glow of the Milky Way itself. No other galaxies would be visible to the naked eye. Ancient civilizations would have developed entirely different mythologies, religions, and scientific theories about the universe. Based on this profound isolation, they would have seen a universe with only one galaxy, one island of light in an infinite sea of darkness, and perhaps concluded that they were the center of all creation, a singular miracle in an empty cosmos. But the void is not truly empty. Dark matter, the mysterious substance that makes up 85% of all matter in the universe, forms invisible scaffolding throughout this region. We cannot see it directly, but its gravitational influence shapes the very fabric of space-time around us. Our instruments detect its presence through subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang itself. It is the ghost in the machine, the silent architect of cosmic structure, holding galaxies together and guiding their dance across billions of years. It is the unseen river that carves the canyon of the cosmos. As we travel deeper into the void, we encounter something unexpected: rogue planets, ejected from their home solar systems by gravitational interactions with passing stars. These orphaned worlds drift through the darkness, no longer warmed by any sun. Their surfaces frozen solid, and their atmospheres collapsed into ice. Some of these planets are larger than Jupiter, others smaller than Earth, but all share the same fate of eternal wandering through the cosmic deep. One rogue planet we encounter tells a particularly haunting story. Its surface shows evidence of ancient oceans, now frozen kilometers thick. Beneath that ice, our scanners detect something remarkable: a subsurface ocean, kept liquid by the planet's own radioactive decay and tidal forces from a long-lost moon. In this hidden sea, completely isolated from any star's light, primitive life forms might still exist, evolved from organisms that survived their world's ejection into space billions of years ago. They would be creatures of darkness and pressure, their biology powered not by sunlight, but by chemical reactions in the planet's core. A civilization of beings who have never seen a star, whose concept of the universe is a dark, warm ocean, and for whom the idea of an outside would be pure fantasy. The void also contains the remnants of ancient galaxy collisions, tidal streams of stars, stretched across millions of light years, mark the paths where smaller galaxies were torn apart by the gravity of larger ones. These stellar graveyards tell the violent history of cosmic evolution, where galaxy clusters grow by cannibalizing their smaller neighbors in a process that continues to this day. We pass through regions where the cosmic web itself is visible: vast filaments of dark matter and ordinary matter that connect galaxy clusters across hundreds of millions of light years. These structures formed in the early universe, when matter first began to clump together under the influence of gravity. They are the highways along which galaxies travel, the channels through which matter flows from one region of the universe to another. The silence here is absolute, broken only by the faint whisper of cosmic rays. High-energy particles traveling at nearly the speed of light, accelerated by unknown processes in the violent hearts of distant galaxies. These particles are the ghosts of ancient explosions, messengers from a more violent time, and they are the only sound in this vast, empty cathedral. Something magnificent appears in the distance. A faint, diffuse glow that slowly resolves into a city of light. A galaxy cluster, containing hundreds of individual galaxies, each one an island universe in its own right. The Virgo cluster spans 13 million light-years across space, containing more than 300 galaxies bound together by gravity in a cosmic dance that has continued for billions of years. As we approach this stellar metropolis, the scale becomes overwhelming. Each galaxy contains hundreds of billions of stars, and many of these galaxies are larger than our own Milky Way. Some are elegant spirals with arms that sweep through space like frozen fireworks. Others are massive ellipticals that glow with the combined light of 1 trillion ancient suns, their reddish hue a sign of their advanced age. And still others are irregular dwarfs, twisted and distorted by the gravitational pull of their larger neighbors, their stars scattered like dust in the wind. The largest galaxy in the cluster, Messier 87, dominates the central region like a cosmic giant. This massive elliptical galaxy contains over 1 trillion stars and harbors one of the most powerful black holes ever discovered. The black hole at its center is so massive that it contains the equivalent of 6.5 billion suns. A gravitational singularity that has consumed entire star systems for breakfast. And it is actively feeding on surrounding matter, creating jets of plasma that shoot out from its poles at nearly the speed of light. These jets extend for thousands of light years, creating a cosmic lighthouse that can be seen from billions of light years away. The energy released by matter falling into this black hole is so enormous that it heats the surrounding gas to millions of degrees, creating a hot, glowing atmosphere that pervades the entire galaxy cluster. A celestial bonfire that sterilizes any potential life for light years around. Between the galaxies, we discover an invisible ocean of superheated gas, heated to temperatures of 50 million degrees Celsius by the gravitational energy of the cluster itself. This intergalactic medium contains more matter than all the stars in all the galaxies combined. Yet, it is so diffuse that it is completely invisible to the naked eye. Only our most sensitive instruments can detect its presence through the X-rays it emits as it radiates away its enormous heat. The cluster is also filled with dark matter, which makes up about 85% of all the matter here. This mysterious substance forms an invisible scaffolding that holds the entire cluster together, preventing the galaxies from flying apart despite their enormous speeds. Some galaxies are moving through the cluster at over 1,000 kilometers per second, fast enough to travel from Earth to the Moon in just 6 minutes. Yet they are trapped in this gravitational web, destined to orbit for eternity. As we navigate through this cosmic city, we witness ongoing galactic interactions. Smaller galaxies are being torn apart by tidal forces, their stars stripped away to form long streamers that will eventually be absorbed by larger galaxies. This is galactic cannibalism on a massive scale, where the strong devour the weak in a process that has shaped the evolution of galaxies since the early universe. The gravitational forces here are so intense that they bend light itself, creating gravitational lenses that magnify and distort the images of even more distant galaxies lying behind the cluster, giving us a warped, fisheye view of the deeper cosmos. We witness something extraordinary: 2 galaxies locked in a gravitational death spiral, their collision unfolding over hundreds of millions of years. The antennae galaxies, once separate and distinct spiral galaxies, are now merging in a cosmic catastrophe that will reshape both systems completely. Their spiral arms have been stretched and distorted into long tidal tails that extend for hundreds of thousands of light years, resembling the antennae of a cosmic insect. The collision zone is a stellar nursery of unprecedented violence. Gas clouds from both galaxies are smashing together at speeds of hundreds of kilometers per second, compressing and heating the interstellar medium until it reaches temperatures where new stars can form. The rate of star formation here is 10 times higher than in normal galaxies, creating brilliant clusters of young, hot stars that burn with the intensity of blue-white diamonds. But star formation is not the only consequence of this cosmic collision. The gravitational chaos is also feeding the supermassive black holes at the centers of both galaxies. As gas spirals inward toward these cosmic monsters, it heats up and glows with X-ray radiation, creating some of the brightest objects in the universe. These active galactic nuclei pump enormous amounts of energy into their surroundings, creating jets of plasma that extend far beyond the visible galaxies themselves. The merger is also creating something entirely new: globular clusters, dense balls of stars that will survive long after the collision is complete. These stellar cities contain hundreds of thousands of stars packed into regions just a few dozen light years across. They are among the oldest objects in the universe, and new ones are being born in the chaos of this galactic collision. As we watch this cosmic catastrophe unfold, we realize we are seeing the future of our own galaxy. In approximately 4 billion years, the Milky Way will collide with the Andromeda Galaxy in a similar cosmic dance. The collision will take place over hundreds of millions of years, gradually reshaping both galaxies into something entirely new. A giant elliptical galaxy that will dominate the local group. The space between the colliding galaxies is not empty. It is filled with streams of stars that have been torn from their home galaxies by tidal forces. These stellar refugees will wander through intergalactic space for billions of years, no longer bound to any particular galaxy. Some will eventually be captured by other galaxies, while others will drift alone through the cosmic void forever. Their light a faint, lonely echo of a home they can never return to. Despite the apparent violence of the collision, individual stars rarely collide with each other. The distances between stars are so vast that most will simply be redistributed into new orbits around the merged galaxy's center. However, many planetary systems will be disrupted, their planets flung into new orbits or ejected from their home systems entirely, sent on a one-way journey into the cold, dark void. The collision is also creating something beautiful: shock waves that compress the interstellar medium and cause it to glow with brilliant colors. These cosmic fireworks paint the merger zone in shades of red, blue, and green, creating one of the most spectacular sights in the universe. A testament to the fact that even in destruction, there is a kind of terrible, awe-inspiring beauty. We encounter our first truly alien world, a planet orbiting a binary star system where the very nature of day and night challenges everything we thought we knew about planetary environments. This world, twice the size of Earth, experiences a complex cycle of illumination as it orbits two stars locked in their own gravitational dance. The primary star is a yellow dwarf, similar to our Sun, but its companion is a red dwarf that burns with a cooler, dimmer light, a crimson eye in the sky. As the planet moves through its orbit, it experiences periods of single-star days, double-star days, and even brief, breathtaking eclipses when one star passes in front of the other. The result is a world where the concept of a standard day has no meaning, where the inhabitants must adapt to constantly changing patterns of light and darkness. The sky here is never truly dark, but shifts from a bright golden yellow to a deep blood-red twilight, a perpetual state of dawn or dusk. The planet's surface reflects this chaotic illumination cycle. Vast regions are covered in crystalline formations that act like natural solar collectors, gathering and storing light energy during the brightest periods and releasing it slowly during the darker phases. These crystal forests create a landscape that shimmers and glows with accumulated starlight, painting the world in constantly shifting colors, a living kaleidoscope that breathes light. The atmosphere here is unlike anything in our solar system. It contains high concentrations of noble gases that create spectacular auroras when charged particles from the binary stars interact with the planetary magnetic field. These auroras are not confined to the polar regions like on Earth. They dance across the entire sky in ribbons of green, purple, and gold that can be seen even during the day. A constant, silent celestial ballet. Life on this world has evolved in remarkable ways. The dominant species are silicon-based organisms that incorporate the planet's crystals into their biological structures. They can photosynthesize using light from both stars simultaneously, making them incredibly efficient at converting stellar energy into biological energy. During the double star periods, they grow rapidly, storing excess energy in specialized organs. During the darker periods, they enter a state of reduced activity, living off their stored energy reserves, their crystalline bodies glowing faintly in the dim red light of the smaller star. The planet's oceans are equally extraordinary. They contain dissolved minerals that make the waters slightly luminescent, creating seas that glow with their own internal light. Underwater, entire ecosystems have evolved around chemosynthetic organisms that derive energy from the planet's geological activity rather than from starlight. These deep-sea communities exist in complete independence from the surface world, thriving in eternal darkness beneath the glowing waters. A hidden biosphere that has never known the touch of a sun. The binary star system itself is evolving. The two stars are slowly spiraling inward toward each other, their orbital decay caused by the emission of gravitational waves. In approximately 2 billion years, they will merge in a spectacular collision that will briefly outshine entire galaxies. When that happens, this remarkable world will be vaporized in seconds, its complex ecosystems and beautiful crystal landscapes reduced to their component atoms. But for now, the planet continues its complex dance around its twin suns, a testament to the incredible diversity of worlds that exist in the universe. As we leave this system behind, we carry with us the knowledge that life finds ways to adapt to conditions that would seem impossible to Earth-based organisms, and that the universe is far more imaginative in its creations than we could have ever dreamed. We approach a stellar graveyard, where the remnants of dead stars create one of the most dangerous regions in the galaxy. Here, neutron stars, the collapsed cores of massive stars that exploded as supernova, spin at incredible speeds while generating magnetic fields trillions of times stronger than Earth's. One neutron star captures our attention immediately. It is only 20 kilometers across, smaller than most cities. Yet it contains more mass than our entire sun. A single teaspoon of neutron star material would weigh 6 billion tons on Earth. The gravity here is so intense that the escape velocity is nearly half the speed of light, and time itself runs noticeably slower than in normal space. This particular neutron star is a pulsar, spinning 30 times per second while beaming lighthouse-like streams of radiation from its magnetic poles. Each pulse arrives with clockwork precision, more accurate than the most precise atomic clocks humans have ever built. The beams sweep across space like the rotating beam of a lighthouse, and when they point in our direction, our instruments detect bursts of radio waves, X-rays, and gamma rays. The space around the pulsar is filled with a wind of charged particles accelerated to nearly the speed of light. This pulsar wind creates a bubble of high-energy plasma that extends for light years in all directions, heating the surrounding interstellar medium to millions of degrees and creating a glowing nebula that can be seen from thousands of light years away. As we maintain a safe distance, we observe the pulsar's incredible power. In just 1 second, it releases more energy than our sun produces in an entire month. This energy comes from the neutron star's rotation. It is literally spinning down, converting its rotational energy into the radiation that we detect as pulses over millions of years. The pulsar will gradually slow down until it becomes a quiet, dark neutron star, invisible except for its gravitational effects. Near the pulsar, we encounter something even more exotic, a magnetar, a neutron star with a magnetic field so strong that it defies comprehension. The magnetic field here is a quadrillion times stronger than Earth's magnetic field, powerful enough to strip electrons from atoms at a distance of 1,000 kilometers. If you could somehow survive getting within 1,000 kilometers of a magnetar, the magnetic field would distort your atoms, stretching them into thin, needle-like shapes aligned with the field lines. Magnetars are rare and unstable. They occasionally experience starquakes, sudden rearrangements of their crystalline crusts that release more energy in 1/10 of a second than our sun produces in a year. These starquakes create bursts of gamma rays so intense that they can affect Earth's atmosphere from thousands of light years away. The region also contains isolated black holes, stellar corpses so dense that nothing, not even light, can escape their gravitational pull. These invisible monsters can only be detected by their gravitational effects on nearby matter, creating accretion disks of superheated gas that spiral inward while glowing with X-ray radiation. This is where massive stars come to die, creating some of the most extreme environments in the universe. A cosmic cemetery where the laws of physics are pushed to their absolute limits. We enter a region where space itself seems to be boiling with energy. Here, the fabric of space-time is constantly fluctuating with quantum foam, virtual particles that pop into existence and annihilate each other in time frames so brief that they seem to violate the conservation of energy. This is the quantum vacuum, and it is anything but empty. At the smallest scales, space and time become grainy and uncertain. The smooth fabric of space-time that we experience in everyday life breaks down into a churning sea of quantum fluctuations. Virtual photons, electron-positron pairs, and other exotic particles constantly appear and disappear, borrowing energy from the vacuum itself and paying it back before the universe notices the debt. These quantum fluctuations have real, measurable effects. They create a subtle force called the Casimir effect, where two parallel plates placed very close together in a vacuum will experience an attractive force due to the quantum fluctuations of the electromagnetic field. The space between the plates contains slightly fewer virtual photons than the space outside, creating a pressure difference that pushes the plates together. As we travel deeper into this quantum realm, we encounter something extraordinary, a region where the expansion of the universe itself is accelerating. Dark energy, the mysterious force that makes up 70% of all energy in the universe, is stretching space itself at an ever-increasing rate. This cosmic acceleration means that distant galaxies are moving away from us faster and faster, and eventually, they will recede so quickly that their light will never reach us. The nature of dark energy remains one of the greatest mysteries in cosmology. It might be a property of space itself, a quantum field that permeates all of reality, or something even more exotic that we do not yet understand. What we do know is that it is winning the cosmic battle against gravity, driving the universe toward a cold, dark future, where galaxies will be isolated islands in an ever-expanding sea of emptiness. In this region, we also encounter cosmic strings, theoretical one-dimensional defects in space-time that might have formed during the first moments after the Big Bang. These cosmic strings are thinner than a proton, but can stretch across entire galaxies, containing enormous amounts of energy and creating gravitational effects that can bend light and distort space around them. If cosmic strings exist, they would be among the most exotic objects in the universe. They would vibrate like guitar strings, creating gravitational waves that could be detected by future generations of instruments. Some theories suggest that cosmic strings could even be used as cosmic highways, allowing advanced civilizations to travel vast distances by following the strings through space. The quantum vacuum also contains the possibility of spontaneous symmetry breaking, where the fundamental forces of nature might suddenly change their properties. This could create bubble universes with different physical laws, where the speed of light, the strength of gravity, or even the number of spatial dimensions might be different from our own universe. Here, at the intersection of quantum mechanics and cosmology, we glimpse the deepest mysteries of existence itself. A place where the rules of reality are not fixed, but fluid, and where anything seems possible. We discover a cosmic phenomenon that challenges our understanding of physics itself. A region where time flows differently due to extreme gravitational fields. Here, the curvature of space-time is so severe that hours pass like minutes, and the very concept of simultaneity breaks down completely. The source of this temporal distortion is a rotating black hole of intermediate mass, spinning so rapidly that it drags space-time around with it like honey. This effect, called frame dragging, creates a region where it is impossible to remain stationary relative to distant stars. Everything in the vicinity is forced to rotate along with the black hole, caught in a cosmic whirlpool of twisted space-time. As we approach the ergosphere, the region outside the black hole's event horizon where space-time is being dragged around, we experience something unprecedented. Our clocks begin to run slow compared to the time we left behind. Minutes stretch into hours, and hours into days. If we were to spend just 1 hour in the deepest part of the ergosphere, decades would pass in the outside universe. We would return to a future we never lived, a ghost in our own timeline. The black hole itself is a monster, containing the mass of 10,000 suns compressed into a region smaller than a city. Its event horizon, the point of no return, appears as a perfect sphere of absolute blackness, surrounded by a swirling disk of superheated matter that glows with the intensity of 1 billion stars. This accretion disk is where matter spirals inward toward its doom, heating up to temperatures of millions of degrees as it falls toward the black hole. But the most remarkable feature of this system is the jets of plasma that shoot out from the black hole's poles at 99% the speed of light. These relativistic jets extend for thousands of light years, creating cosmic beacons that can be seen from across the universe. The energy for these jets comes from the black hole's rotation itself, through a process that extracts energy from the spinning space-time around the black hole. Near the black hole, we encounter something that should not exist according to our current understanding of physics matter that appears to be falling upward, away from the black hole's gravity. This is an illusion created by the extreme curvature of space-time, where the very concepts of up and down lose their meaning. What we are seeing is matter following geodesics, the straightest possible paths through curved space-time, that appear curved to our outside perspective. The gravitational field here is so strong that it creates multiple images of distant objects through gravitational lensing. Stars behind the black hole appear as rings of light, their images distorted and magnified by the black hole's gravity. We can see the same star from multiple angles simultaneously, as light from the star follows different paths around the black hole to reach us. In this region, the fundamental nature of space and time becomes apparent. They are not separate entities, but part of a single, unified space-time fabric that can be stretched, compressed, and twisted by the presence of matter and energy. The black hole is not just an object in space. It is a wound in the fabric of reality itself, a place where our understanding of the universe breaks down completely. We encounter the most beautiful and terrifying sight in the universe, a star in the process of dying. Its outer layers being blown away in a spectacular planetary nebula that paints space in brilliant colors. The dying star, a white dwarf no larger than Earth, but containing the mass of our sun, sits at the center of an expanding shell of glowing gas that stretches for light years in all directions. The nebula itself is a masterpiece of cosmic art. Shells of different gases glow in distinct colors: hydrogen in red, oxygen in green and blue, nitrogen in deep red, creating intricate patterns that resemble flowers, butterflies, or abstract sculptures. These colors are created by the intense ultraviolet radiation from the white dwarf, which ionizes the surrounding gas and causes it to fluoresce like a cosmic neon sign. The white dwarf at the center is the exposed core of what was once a star, similar to our sun. For billions of years, it burned hydrogen and helium in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But eventually, the fuel ran out, and the star began its death throes. As the nuclear fires died down, gravity began to win the battle. The star's core collapsed, while its outer layers expanded, creating a red giant that was hundreds of times larger than the original star. For millions of years, the red giant pulsed and varied in brightness, shedding its outer layers in a series of stellar winds that created the beautiful nebula we see today. The white dwarf itself is an object of incredible density. A cubic centimeter of white dwarf material would weigh as much as a car on Earth. The surface gravity is so intense that a person standing on a white dwarf would weigh about 1,000,000 times more than they do on Earth. The surface temperature is over 50,000 degrees Celsius, hot enough to ionize any material that comes near it. But this white dwarf is not alone. It has a companion star, a red dwarf that orbits close enough to have matter stripped away by the white dwarf's gravity. This stolen matter spirals inward, forming an accretion disk that glows with X-ray radiation. Periodically, enough matter accumulates on the white dwarf's surface to trigger a thermonuclear explosion, a nova that can briefly outshine entire galaxies. A final violent burst of light from a dying star. The nebula is also a recycling plant for the universe. The gas being expelled contains heavy elements forged in the dying star's core: carbon, nitrogen, oxygen, and other elements essential for life. These elements will eventually be incorporated into new stars and planets, continuing the cosmic cycle of death and rebirth that has been ongoing since the first stars formed billions of years ago. As we watch this stellar death unfold, we are witnessing the fate that awaits our own sun. In about 5 billion years, the sun will expand into a red giant, engulfing the inner planets before finally shedding its outer layers and leaving behind a white dwarf surrounded by a planetary nebula that will glow for thousands of years. A final, beautiful monument to a star that once gave life. We drift into a region where space itself becomes a lens, bending and focusing light from distant galaxies through the sheer power of gravity. Here, a massive galaxy cluster acts as a cosmic magnifying glass, its immense gravitational field warping space-time so severely that it creates multiple, distorted images of the same background galaxies, stretched into glowing arcs that paint the darkness with impossible geometry. The cluster contains over 1,000 galaxies, each one an island universe in its own right, bound together by the invisible grip of dark matter. But it is not the visible galaxies that create the lensing effect. It is the dark matter halo that surrounds them. A massive concentration of invisible matter that outweighs all the visible stars and gas by a factor of 10 to 1. As light from distant galaxies travels toward us, it must pass through the curved space-time created by the cluster's enormous mass. The light follows the straightest possible path through this curved space. But from our perspective, these straight paths appear curved, creating the spectacular arcs and rings we observe. Some background galaxies appear as complete Einstein rings, perfect circles of light that surround the lensing cluster like cosmic halos. The gravitational lensing effect is so powerful that it allows us to see galaxies that would otherwise be completely invisible. The cluster's gravity magnifies the light from these distant galaxies by factors of 10, 50, or even 100, making them appear brighter and larger than they actually are. This cosmic telescope effect lets us observe galaxies as they existed when the universe was less than 1 billion years old, providing a window into the early stages of cosmic evolution. One particularly spectacular lensed galaxy appears as a giant arc stretched across half the sky. This galaxy is so distant that its light has traveled for over 12 billion years to reach us, showing us what galaxy formation looked like when the universe was in its infancy. The galaxy appears distorted and fragmented, broken into multiple images by the complex gravitational field of the cluster. The lensing effect also reveals the true distribution of matter in the cluster. By measuring how the background galaxies are distorted, we can map the invisible dark matter that dominates the cluster's mass. This dark matter mapping shows that the cluster is not a single, uniform structure, but rather a complex web of dark matter clumps and filaments that stretches across millions of light years. The cluster itself is a violent place. Galaxies are constantly colliding and merging, their stars scattered and their gas stripped away by the hot, dense medium that fills the space between galaxies. This intergalactic medium is heated to temperatures of over 50 million degrees by the gravitational energy of the cluster, creating a vast atmosphere of X-ray emitting plasma. The cluster is also home to some of the most massive black holes in the universe. At the center of the dominant galaxy, a supermassive black hole containing billions of solar masses is actively feeding on the surrounding gas, creating jets of plasma that extend for hundreds of thousands of light years and heat the cluster's atmosphere. This is gravity as a cosmic architect, shaping the very fabric of space-time and creating natural telescopes that reveal the deepest secrets of the universe. A silent, invisible force that paints the cosmos with light from a time before time. We witness the birth of something that should not exist according to our current understanding of physics, a primordial black hole. Formed not from the collapse of a massive star, but from the extreme density fluctuations that existed in the first moments after the Big Bang. This cosmic relic is a window into the very early universe, when the laws of physics were still being written and the fundamental forces were unified in ways we can barely comprehend. The primordial black hole is tiny compared to the stellar mass black holes we have encountered so far. It contains only the mass of a small asteroid, compressed into a region smaller than a proton. But its small size makes it incredibly exotic. with properties that bridge the gap between general relativity and quantum mechanics in ways that challenge our deepest theoretical understanding. According to quantum mechanics, the black hole should be evaporating through a process called Hawking radiation. The curved space-time around the black hole creates virtual particle pairs at the event horizon, and occasionally, one particle from each pair falls into the black hole while the other escapes. This process slowly reduces the black hole's mass, causing it to shrink and eventually disappear in a final burst of radiation. But this primordial black hole is behaving strangely. Instead of evaporating as theory predicts, it appears to be growing, accreting dark matter from its surroundings at a rate that exactly balances the mass loss from Hawking radiation. The black hole has reached a state of equilibrium, maintaining a constant mass while existing in a delicate balance between quantum evaporation and classical accretion. A cosmic stalemate between two of the universe's most powerful forces. The space around the black hole is a laboratory for extreme physics. The gravitational field is so intense that it creates measurable effects on the passage of time itself. Clocks near the black hole run slower than those in normal space, and the wavelength of light is stretched as it climbs out of the gravitational well. The black hole's accretion of dark matter creates a unique observational signature. As dark matter particles fall toward the event horizon, they interact with each other through processes that are normally too weak to detect. The extreme environment near the black hole amplifies these interactions, creating a faint glow of exotic particles that provides our first direct observation of dark matter's true nature. The primordial black hole also serves as a natural particle accelerator. The intense gravitational field accelerates infalling matter to speeds approaching the speed of light, creating conditions that existed nowhere else in the universe since the first moments after the Big Bang. The collision of these high-energy particles recreates the physics of the early universe, providing insights into the fundamental nature of matter and energy. As we observe this cosmic relic, we realize that we are looking at a fragment of the universe's birth, a piece of the Big Bang that has survived for over 13 billion years. The black hole carries information about the conditions that existed when the universe was less than a second old, when the temperature was billions of degrees and the density was greater than that of atomic nuclei. This is cosmology in its purest form, where the smallest objects reveal the grandest truths about the nature of reality itself. We approach a cosmic phenomenon that exists at the very edge of possibility, a white hole, the theoretical opposite of a black hole, where matter and energy are expelled rather than consumed. If black holes are cosmic drains that swallow everything that comes near them, white holes are cosmic fountains that spew matter and energy into space at incredible rates. The white hole appears as a brilliant point of light that outshines entire star clusters, surrounded by expanding shells of matter moving at significant fractions of the speed of light. Unlike black holes, which have event horizons that trap everything inside, white holes have event horizons that prevent anything from entering. Matter and energy can only flow outward, creating a cosmic geyser that has been erupting for billions of years. The physics of white holes is even more exotic than that of black holes. According to general relativity, white holes are mathematically valid solutions to Einstein's field equations, but they violate the second law of thermodynamics by creating, rather than destroying information. They represent a reversal of time's arrow, where the normal flow of cause and effect is turned upside down. The white hole's origin is shrouded in mystery. One possibility is that it formed from the time-reversed collapse of a massive star, where instead of matter falling inward to create a black hole, matter exploded outward from a point of infinite density. Another theory suggests that white holes might be the exit points of black holes from other universes, connected through cosmic wormholes that allow matter to flow from one universe to another. The matter being expelled from the white hole is unlike anything we have seen before. It consists of exotic particles that do not exist under normal conditions, particles that carry negative energy, antimatter in configurations that should not be stable, and even hypothetical particles that exist only in the most advanced theoretical models. This matter creates an expanding bubble of space that glows with energy across the entire electromagnetic spectrum. The white hole's gravitational field is equally bizarre. While black holes curve space-time inward, creating gravitational wells that trap matter, white holes curve space-time outward, creating gravitational hills that repel matter. The closer you get to a white hole, the stronger the repulsive force becomes, making it impossible to approach the event horizon from the outside. The white hole is also a source of gravitational waves. But these waves are different from those produced by black hole mergers. Instead of the characteristic chirp of objects spiraling inward, white hole gravitational waves have a complex pattern that reflects the chaotic nature of matter being expelled at high speeds. These waves carry information about the interior structure of the white hole and the exotic physics that governs its behavior. The white hole's existence challenges our understanding of causality and the nature of time itself. If white holes can exist, then the universe might be far stranger than we imagine, with regions where time flows backward and effect precedes cause. The white hole represents a cosmic paradox, an object that should not exist according to our current understanding of physics. Yet, here it is, defying our expectations and forcing us to reconsider the fundamental laws of nature. This is where theoretical physics meets cosmic reality, where the impossible becomes possible in the extreme environments of the universe. We encounter a structure so vast that it challenges our understanding of what constitutes a single object in the universe, a cosmic web filament, stretching across 500 million light-years, connecting galaxy clusters in a network of dark matter and ordinary matter that forms the backbone of cosmic structure. The filament is not empty space, but a river of matter flowing through the universe. Dark matter particles, invisible to our eyes but detectable through their gravitational effects, form the filament's core structure. Along this dark matter highway, ordinary matter, hydrogen and helium gas, flows like a cosmic river, feeding the galaxy clusters at the filament's intersections. As we travel along the filament, we observe the cosmic web in all its glory. The universe is not uniformly filled with galaxies, but rather organized into a vast network of filaments, sheets, and voids that resembles a three-dimensional spiderweb. The filaments connect dense nodes where galaxy clusters form, while the voids between them are vast regions of near-empty space that can span hundreds of millions of light-years. The filament we are following is particularly active. Gas flowing along its length is being heated by shock waves created by the gravitational collapse of the structure itself. These shock waves accelerate particles to high energies, creating a faint glow of radio emission that can be detected by the most sensitive telescopes. The filament is essentially a cosmic particle accelerator, stretching across hundreds of millions of light-years. At regular intervals along the filament, we encounter galaxy groups and clusters forming at the intersections of multiple filaments. These cosmic cities are where the majority of galaxies in the universe reside, fed by the steady flow of matter along the filament highways. The largest clusters form at the intersections of the most massive filaments, creating superclusters that contain thousands of galaxies bound together by gravity. The filament also serves as a conveyor belt for galaxy evolution. Small galaxies formed in the quieter regions of the filament are gradually drawn toward the denser cluster environments, where they experience ram pressure stripping tidal interactions, and eventually merge with larger galaxies. This cosmic urbanization process transforms spiral galaxies into elliptical galaxies and determines the final properties of the galaxy population. The structure of the cosmic web itself tells the story of the universe's evolution. The filaments formed from tiny density fluctuations in the early universe, regions where matter was slightly denser than average over billions of years. Gravity amplified these fluctuations, drawing matter into ever denser concentrations along the filament network. The pattern we see today is a fossil record of conditions in the universe when it was less than 1 million years old. The filament is also a highway for cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. These particles follow the magnetic field lines that thread through the filament, creating a cosmic superhighway that connects distant regions of the universe. Some of these cosmic rays will eventually reach Earth, carrying information about the most violent events in the universe. This is architecture on the largest scales possible, where the universe organizes itself into structures that span significant fractions of the observable cosmos. We approach the event horizon of a supermassive black hole, the point of no return where the escape velocity equals the speed of light and the normal laws of physics begin to break down. This cosmic monster contains the mass of 4 billion suns, compressed into a region smaller than our solar system, creating a gravitational field so intense that it warps space-time into impossible geometries. The approach to the event horizon is a journey through increasingly extreme physics. Time dilation becomes severe as we descend deeper into the gravitational well. Minutes for us correspond to hours in the outside universe. Light from distant stars appears blue-shifted ahead of us and red-shifted behind us, creating a tunnel of distorted starlight that shrinks as we approach the point of no return. The black hole's accretion disk spreads around us like a cosmic hurricane, with matter spiraling inward at thousands of kilometers per second. The disk glows with the heat of friction as gas particles collide and compress, reaching temperatures of millions of degrees. The inner regions of the disk shine with X-ray radiation, while the outer regions glow with optical and infrared light. Jets of plasma shoot out from the black hole's poles at 99% the speed of light, creating cosmic lighthouses that extend for thousands of light years. These jets are powered by the black hole's rotation, which drags space-time around with it and creates a region called the ergosphere, where it is impossible to remain stationary relative to distant stars. As we cross the event horizon, we experience something that has never been directly observed: the interior of a black hole. Contrary to popular belief, crossing the event horizon is not immediately fatal. The horizon appears as a one-way membrane through which we can pass, but from which no signal can ever return to the outside universe. To an outside observer, we would appear to freeze at the event horizon, our image redshifted into invisibility. Inside the black hole, space-time is so severely curved that the normal concepts of space and time lose their meaning. The singularity at the center appears to be both everywhere and nowhere, a point of infinite density where the laws of physics as we know them cease to apply. Some theories suggest that the singularity might be replaced by exotic structures, cosmic strings, naked singularities, or even gateways to other universes. The interior of the black hole is filled with the ghosts of everything that has ever fallen in stars, planets, gas clouds, and even light itself, all compressed and distorted by the extreme curvature of space-time. This information is not destroyed, but transformed in ways that challenge our understanding of quantum mechanics and general relativity. The black hole's interior might also be larger than it appears from the outside. The extreme curvature of space-time could create additional dimensions or pocket universes that exist within the black hole, but are invisible to outside observers. These regions might harbor exotic forms of matter and energy that exist nowhere else in the universe. This is the ultimate frontier of physics, where the most extreme conditions in the universe create phenomena that exist at the very edge of theoretical possibility. We emerge from the black hole's interior through a phenomenon that should not be possible according to classical physics, a white hole. Connected to the black hole through a cosmic wormhole that serves as a bridge between distant regions of space-time. This Einstein-Rosen bridge allows matter and energy to flow from one location in the universe to another, creating a cosmic shortcut through the fabric of space and time. The wormhole appears as a tunnel of twisted space-time, its walls lined with exotic matter that has negative energy density. This exotic matter is what keeps the wormhole open, preventing it from collapsing under its own gravity. The matter creates a repulsive gravitational effect that pushes outward on the wormhole's walls, maintaining the tunnel's stability against the natural tendency of space-time to heal such extreme distortions. As we travel through the wormhole, we experience the ultimate in cosmic transportation. The journey that would normally take millions of years traveling through normal space is completed in minutes, as we slide through the curved space-time of the wormhole's interior. The walls of the tunnel glow with Hawking radiation, the quantum mechanical emission that results from the interaction between matter and the extremely curved space-time. The wormhole's interior is a place where causality itself becomes questionable. Information can flow backward through time, creating closed time-like curves that allow effects to precede their causes. This violation of causality is what makes wormholes so controversial in theoretical physics. They seem to allow for time travel and the creation of paradoxes that challenge our understanding of the universe's logical structure. The exotic matter that keeps the wormhole open is unlike anything that exists in the normal universe. It has negative energy density, which means it weighs less than nothing and creates a repulsive gravitational effect. This matter might be composed of virtual particles borrowed from the quantum vacuum, or it might be a form of matter that exists only in the extreme conditions found near black holes and other exotic objects. The wormhole connects two regions of space-time that are normally separated by vast distances. The black hole we entered might be in one galaxy, while the white hole we are approaching could be in a completely different galaxy, billions of light years away. This cosmic shortcut allows for instantaneous communication and travel between distant regions of the universe. The white hole that marks the wormhole's exit is the time-reversed version of the black hole we entered. While black holes swallow everything that comes near them, white holes expel matter and energy at tremendous rates. The white hole appears as a brilliant source of light and particles, surrounded by expanding shells of matter that have been ejected from its interior. The wormhole's existence has profound implications for the nature of space and time. If such structures exist, then the universe might be far more connected than we imagine. With networks of wormholes linking distant regions and allowing for the rapid transport of matter, energy, and information across cosmic distances. This is speculative physics at its most extreme, where the boundaries between science and science fiction become blurred in the face of phenomena that challenge our deepest assumptions about reality. We approach a cosmic phenomenon that exists at the intersection of the very large and the very small. A region where quantum mechanics and general relativity collide in spectacular fashion. Here, the quantum foam of space-time becomes visible, creating a seething froth of virtual particles and microscopic black holes that pop into existence and disappear faster than light can travel between them. At the smallest scales, space and time lose their smooth, continuous nature and become discrete and granular. The Planck scale, where distances are measured in units of 10 to the negative 35th meters and time intervals in units of 10 to the negative 43rd seconds, represents the fundamental limit of space-time itself. Below this scale, the very concepts of space and time break down, replaced by something far stranger and more fundamental. The quantum foam is filled with virtual particles that exist for impossibly brief moments before annihilating each other and returning their borrowed energy to the vacuum. These particles are not directly observable, but their effects are real and measurable. They create a background of energy that permeates all of space, contributing to the cosmological constant that drives the accelerating expansion of the universe. Microscopic black holes, smaller than atoms but containing the mass of mountains, appear and disappear in the quantum foam. These primordial black holes are remnants of the extreme conditions that existed in the first moments after the Big Bang, when the universe was so dense that random fluctuations could create black holes from pure energy. Most of these micro-black holes evaporate instantly through Hawking radiation, but some might survive as relics of the early universe. The quantum foam also contains cosmic strings, one-dimensional defects in space-time that are thinner than protons, but potentially billions of light-years long. These strings carry enormous amounts of energy and create gravitational fields that can bend light and distort space around them. If cosmic strings exist, they would be among the most exotic objects in the universe, vibrating like cosmic guitar strings and creating gravitational waves that could be detected by future instruments. The foam is also the birthplace of the fundamental forces of nature. At the Planck scale, the electromagnetic, weak, and strong nuclear forces merge into a single, unified force, creating conditions that existed nowhere else in the universe since the first moments after the Big Bang. The quantum foam is a laboratory for grand unified theories, where the deepest symmetries of nature are revealed. In this region, the boundary between matter and space-time itself becomes meaningless. Particles and the vacuum are interchangeable, with virtual particles constantly being created from nothing and disappearing back into the void. This process is what gives the vacuum its energy and creates the mysterious dark energy that dominates the universe. The quantum foam also contains the information that defines the laws of physics themselves. The fundamental constants of nature, the speed of light, the strength of gravity, the mass of the electron might be encoded in the structure of the foam at the Planck scale. This suggests that the laws of physics are not arbitrary, but are determined by the quantum mechanical properties of space-time itself. This is reality at its most fundamental level, where the distinction between matter and space disappears and the universe reveals its deepest secrets. We witness the birth of a new universe within our own, a cosmic bubble that expands through a process called eternal inflation, creating an entirely separate space-time with its own physical laws and constants. This baby universe appears as a rapidly expanding sphere of space that grows faster than the speed of light, driven by the explosive energy of a false vacuum decay event. The process began with a tiny fluctuation in the quantum foam, a region where the fundamental energy field that drives inflation became unstable. This instability triggered a phase transition, like water suddenly turning to ice, but on a cosmic scale. The energy released by this phase transition created a new region of space-time that began expanding exponentially, doubling in size every fraction of a second. The baby universe is not just a larger version of the space around it. It is a completely separate cosmos with its own unique properties. The fundamental constants of physics might be different there, with different values for the speed of light, the strength of gravity, or the mass of elementary particles. The number of spatial dimensions might even be different. creating a universe where the familiar three dimensions of space are replaced by something completely alien. As the baby universe expands, it becomes causally disconnected from our own cosmos. Information cannot flow between the two universes, making the baby universe essentially unreachable from our perspective. To an observer inside the baby universe, it would appear to be the entire cosmos, with no awareness of the parent universe from which it emerged. The boundary between the two universes is a fascinating region where the laws of physics undergo dramatic changes. Space and time themselves might have different properties on either side of the boundary, creating a cosmic membrane that separates two entirely different realities. The boundary acts like a one-way valve, allowing the baby universe to expand outward while preventing any communication with the parent universe. The inflation process that drives the baby universe's expansion is powered by dark energy, but not the same dark energy that accelerates the expansion of our own universe. This is a more exotic form of energy associated with the false vacuum, a state where the quantum fields that define the fundamental forces of nature are trapped in a high-energy configuration that wants to decay to a lower energy state. The baby universe will eventually undergo its own Big Bang. As the inflation process ends and the energy driving the expansion is converted into matter and radiation, this will create a hot, dense fireball, similar to the one that marked the beginning of our own universe, followed by billions of years of cosmic evolution that might produce stars, galaxies, and even life. The existence of baby universes suggests that our cosmos might be just one member of an infinite multiverse, a vast collection of universes with different physical laws and properties. Some of these universes might be similar to our own, while others might be so alien that they would be completely unrecognizable to us. This is cosmology at its most speculative, where the birth of universes becomes a natural consequence of the quantum mechanical properties of space-time itself. We approach the most distant observable objects in the universe, galaxies so far away that their light has traveled for over 13 billion years to reach us, showing us what the cosmos looked like when it was less than 1 billion years old. These ancient galaxies are time machines, preserving the conditions that existed in the early universe. When the first stars were forming and the cosmic dark ages were finally coming to an end, the galaxies appear as faint, red-shifted smudges of light, their wavelengths stretched by the expansion of the universe itself. What would normally be blue and ultraviolet light from hot, young stars has been shifted into the infrared part of the spectrum, requiring specialized instruments to detect and study these cosmic fossils. The redshift is so extreme that these galaxies are receding from us at speeds approaching the speed of light. These early galaxies are smaller and more chaotic than the grand spiral and elliptical galaxies we see in the modern universe. They are actively forming stars at rates that dwarf anything we observe today, creating new suns at rates hundreds of times faster than the Milky Way. The star formation is so intense that these galaxies shine with the light of billions of massive, short-lived stars that will explode as supernovae within just a few million years. The galaxies are also rich in primordial elements, containing almost no heavy elements beyond hydrogen and helium. This is because they formed before generations of stars had time to create and distribute the carbon, oxygen, silicon, and iron that make up the rocky planets and complex chemistry of the modern universe. The first stars in these galaxies were pure hydrogen and helium, burning with nuclear fires that had never before existed in the cosmos. The supermassive black holes at the centers of these early galaxies are growing rapidly, fed by the abundant gas and ongoing galaxy mergers that characterized this early epoch. These black holes are already millions of times more massive than our Sun, despite forming in an era when the universe was less than 1 billion years old. Their rapid growth challenges our understanding of how such massive objects could form so quickly in the early universe. The space between these early galaxies is filled with a warm, ionized gas that glows with the light of the first stars. This is the epoch of rionization, when the first generation of stars began to shine and their ultraviolet radiation ionized the neutral hydrogen that filled the universe. The process transformed the cosmos from a dark, neutral state to the ionized, transparent universe we see today. The galaxies are connected by streams of dark matter and gas that will eventually merge to form the large-scale structure of the modern universe. We can see the cosmic web in its infancy, with filaments of matter connecting the early galaxies and feeding their rapid growth. This is the universe under construction, building the foundations for the cosmic architecture that will persist for billions of years. As we observe these ancient galaxies, we are looking back in time toward the very edge of the observable universe, approaching the cosmic microwave background radiation that marks the moment when the universe became transparent for the first time. We reach the edge of the observable universe, the cosmic microwave background radiation that marks the moment when the universe became transparent for the first time. This wall of ancient light surrounds us in all directions, a spherical shell of radiation that has been traveling through space for over 13 billion years, carrying information about the conditions that existed when the cosmos was only 380,000 years old. The cosmic microwave background appears as a uniform glow of radiation with a temperature of just 2.7 degrees above absolute zero. This radiation is the cooled remnant of the hot, dense fireball that filled the universe in its earliest moments. When the universe was young, it was so hot and dense that electrons and protons existed as separate particles, creating a cosmic soup that was opaque to light. Photons could not travel far before being scattered by free electrons, making the universe a glowing fog. But as the universe expanded and cooled, it reached a critical temperature where electrons and protons could combine to form neutral hydrogen atoms. This event, called recombination, made the universe transparent for the first time. The photons that had been trapped in the cosmic fog were suddenly free to travel through space, carrying with them a snapshot of the universe's conditions at that moment. The cosmic microwave background is remarkably uniform, varying in temperature by only a few parts in 100,000 across the entire sky. But these tiny variations are incredibly important. They represent the seeds of all the structure we see in the modern universe. Regions that were slightly denser than average eventually grew into galaxy clusters, while regions that were slightly less dense became the cosmic voids that separate them. The patterns in the cosmic microwave background tell us about the fundamental properties of the universe itself. The size and shape of the temperature variations reveal the geometry of space-time, the amount of dark matter and dark energy, and the rate of expansion of the universe. This radiation is a cosmic fossil, preserving information about the universe's birth in exquisite detail. As we study the cosmic microwave background, we can see the signatures of cosmic inflation, the exponential expansion that occurred in the first fraction of a second after the Big Bang. The quantum fluctuations that were stretched to cosmic scales during inflation are visible as the temperature variations in the background radiation. These fluctuations are our best evidence for the inflationary epoch that shaped the early universe. The cosmic microwave background also contains information about the first moments after the Big Bang, when the fundamental forces of nature were unified and the universe existed in states that cannot be recreated in any laboratory. The polarization patterns in the radiation might reveal the signature of primordial gravitational waves, ripples in space-time itself that were created by the violent expansion of the early universe. This is the farthest we can see into the past. The ultimate horizon beyond which the universe becomes opaque to electromagnetic radiation. Beyond this wall of ancient light lies the true beginning of everything. The moment when space and time themselves came into existence and the cosmic story began. We begin our final approach to the Andromeda Galaxy. And the scale of what awaits us becomes overwhelming. This cosmic island contains over 1 trillion stars, 4 times more than our home galaxy. From our vantage point, Andromeda appears as a magnificent spiral structure, its arms sweeping through space in elegant curves that have been shaped by billions of years of galactic rotation. The galaxy's spiral arms are not solid structures, but density waves that move through the galactic disk like ripples on a cosmic pond. These waves compress the interstellar gas as they pass, triggering bursts of star formation that light up the arms with brilliant blue and white stars. The arms appear bright because they contain the youngest, hottest stars in the galaxy, massive giants that burn through their fuel quickly and die in spectacular supernova explosions. Andromeda's central bulge glows with the steady light of ancient red giant stars, some of which formed when the universe was less than half its current age. These stellar elders have watched the galaxy evolve for billions of years, surviving multiple passages through the spiral arms and witnessing the rise and fall of countless generations of stars. The bulge contains over 100 billion stars packed into a region just a few thousand light-years across, creating a stellar density that is thousands of times higher than in our local neighborhood. The galaxy's disk is warped and twisted, distorted by gravitational interactions with its satellite galaxies. This warping creates vertical waves that ripple through the disk like a cosmic flag flapping in the wind. The distortion is evidence of Andromeda's violent past, a history of collisions and mergers that have shaped its current structure. As we approach the galaxy's outer regions, we encounter the extended halo of dark matter that surrounds Andromeda like an invisible cocoon. This halo contains 10 times more mass than all the visible stars combined. Yet it can only be detected through its gravitational effects on the stars and gas within the galaxy. The dark matter halo extends for hundreds of thousands of light-years beyond the visible edge of the galaxy, creating a gravitational influence that reaches almost to our own Milky Way. The galaxy's rotation is unlike anything in our solar system. While planets orbit the sun in orderly, predictable paths, the stars in Andromeda move in complex orbits that are influenced by the galaxy's spiral structure, central black hole, and dark matter distribution. Some stars follow nearly circular paths around the galactic center, while others trace elongated ellipses that take them from the inner regions to the outer edges of the galaxy. Andromeda is also home to a complex ecosystem of satellite galaxies, small stellar systems that orbit the main galaxy like cosmic moons. These satellites are being slowly torn apart by Andromeda's gravity, their stars stripped away to form stellar streams that trace their orbital paths. The largest satellites, including M32 and M110, are massive enough to survive this tidal disruption. But smaller satellites are completely destroyed, their stars absorbed into Andromeda's halo. The galaxy is approaching us at 250,000 miles per hour, destined to collide with our own Milky Way in approximately 4 billion years. This cosmic collision will reshape both galaxies, creating something entirely new and magnificent. We plunge into Andromeda's spiral arms, where stellar nurseries are giving birth to new stars at a rate that dwarfs anything in our own galaxy. These star-forming regions are cosmic cities of creation, where giant molecular clouds collapse under their own gravity to form clusters of hot, young stars that will illuminate the galaxy for millions of years to come. The spiral arms are outlined by brilliant blue supergiant stars, each one dozens of times more massive than our Sun and burning with the intensity of 100,000 suns. These stellar monsters have lifespans measured in millions, rather than billions, of years, living fast and dying young in spectacular supernova explosions that seed the galaxy with heavy elements and trigger the formation of new generations of stars. Between the spiral arms, we encounter the galaxy's older stellar population, a mix of red giant stars and main sequence stars like our own Sun. These stars follow more sedate orbits around the galactic center, their motion governed by the galaxy's overall gravitational field, rather than the density waves that define the spiral structure. This is where the galaxy's long-term stellar evolution plays out, with stars slowly aging and evolving over billions of years. The interstellar medium in Andromeda is a complex web of gas and dust that serves as the raw material for future star formation. Hot, ionized gas from supernova explosions and stellar winds creates vast bubbles of million-degree plasma that extend for hundreds of light years. These superbubbles are connected by networks of cooler gas filaments that channel material between different regions of the galaxy. Dust lanes thread through the spiral arms like cosmic highways, marking the densest concentrations of interstellar matter. These dust lanes are where the galaxy's chemical evolution takes place, with heavy elements from dying stars mixing with primordial hydrogen and helium to create the complex chemistry necessary for planet formation and life. The dust grains themselves are cosmic factories, catalyzing chemical reactions that would be impossible in the vacuum of space. The galaxy's magnetic field permeates the entire disk, creating invisible highways that guide the flow of charged particles and cosmic rays. This magnetic field is generated by the motion of ionized quark in the galactic disk, creating a dynamo effect that amplifies and sustains the field over billions of years. The field lines follow the spiral structure of the galaxy, creating a complex pattern that influences everything from star formation to the propagation of cosmic rays. Andromeda's spiral arms are also home to some of the largest star-forming complexes in the local universe. These giant HII regions, ionized by the radiation from massive star clusters, glow with the characteristic red light of hydrogen emission. Some of these regions are so large that they would span significant fractions of our own galaxy's disk, containing enough material to form millions of stars like our Sun. The spiral arms are not permanent features, but transient patterns that rotate through the galaxy at a different speed than the stars themselves. This creates a cosmic traffic jam effect, where stars and gas are compressed as they enter the arms and then spread out as they exit. This compression triggers the star formation that makes the arms so bright and beautiful. We approach the heart of Andromeda, where a supermassive black hole containing the mass of 100 million suns dominates the galactic center. This cosmic monster is 25 times more massive than the black hole at the center of our own galaxy, creating a gravitational influence that shapes the motion of billions of stars across the central regions of Andromeda. The galactic center is a place of extreme stellar density, where stars are packed thousands of times more closely than in our solar neighborhood. Here, close encounters between stars are common, leading to exotic stellar interactions that are virtually impossible in the galaxy's outer regions. Binary star systems are torn apart by gravitational interactions, while single stars can be flung out of the galaxy entirely by close encounters with the central black hole. The black hole itself is surprisingly quiet compared to the active galactic nuclei we have encountered elsewhere in the universe. It is not actively feeding on large amounts of material, which means it is not producing the brilliant jets and intense radiation that characterize quasars and other active galaxies. Instead, Andromeda's central black hole exists in a state of relative dormancy, occasionally flaring up when a star or gas cloud ventures too close. The galactic center is surrounded by a nuclear star cluster, a dense concentration of stars that formed from gas that was funneled toward the galaxy's center by gravitational instabilities. This cluster contains millions of stars packed into a region just a few light years across, creating a stellar environment unlike anything else in the galaxy. The stars here are predominantly old and metal-rich, formed from gas that had been enriched by previous generations of stellar evolution. The central regions of Andromeda also contain a complex network of gas streams and dust lanes that spiral inward toward the black hole. These structures are the galaxy's circulatory system, channeling material from the outer regions toward the center, where it can fuel star formation or feed the central black hole. The gas flows are shaped by the galaxy's bar structure, an elongated concentration of stars that funnels material inward through gravitational torques. The black hole's gravitational influence extends far beyond its immediate vicinity, affecting the orbits of stars throughout the central bulge of the galaxy. The stellar orbits here are complex and chaotic, influenced by the black hole's gravity, the galaxy's bar structure, and the gravitational effects of the dense star clusters surrounding the black hole. Some stars follow highly eccentric orbits that take them from the outer regions of the bulge to within a few light years of the black hole itself. The galactic center is also home to some of the galaxy's most exotic stellar populations. Here we find populations of blue straggler stars, objects that appear younger than they should be based on their location in such an old stellar environment. These stars have been rejuvenated by stellar mergers or mass transfer from companion stars, giving them a second lease on life in the crowded environment of the galactic center. This is the engine room of the galaxy, where the central black hole's gravity orchestrates the complex dance of billions of stars and shapes the galaxy's overall structure and evolution. We discover something extraordinary in Andromeda's halo, a vast graveyard of disrupted satellite galaxies. Their stars scattered in long tidal streams that wrap around the galaxy like cosmic spiderwebs. These stellar streams are the fossil remains of smaller galaxies that were torn apart by Andromeda's gravity. Their stars redistributed throughout the galactic halo in intricate patterns that tell the story of the galaxy's violent past. The most spectacular of these streams is the giant stellar stream, a river of stars that extends for hundreds of thousands of light years and contains the remnants of what was once a substantial dwarf galaxy. The stream is so large that it wraps around Andromeda multiple times, creating a complex